moviendo un sistema, pero sí saber dónde está, o al revés, saber su velocidad, pero no su ubicación. Pero Frank desarrolló un método para saber ambos, la velocidad y la posición. Lo logró analizando un sistema en su transición de fase. Para este tipo de análisis se necesitan modelos teóricos muy complejos. Frank describe a la mecánica cuántica como una técnica matemática especialmente capaz de describir a la naturaleza, y sus investigaciones sobre la teoría algebraica de la dispersión las aplicó en este campo. Octavio Novaro Peñalosa fue físico y miembro del Colegio Nacional desde 1995. Una de las ramas que más le debe a Novaro es la industria petroquímica por sus estudios sobre fuerzas intermoleculares y catálisis teórica. Los catalizadores son partículas muy pequeñas de metales preciosos y Novaro los describía como piedras más pequeñas que las aspirinas, con el poder de acelerar las interacciones entre las moléculas del hidrocarburo. Y el resultado era genial, reacciones químicas en menor tiempo, lo que implicaba usar menos energía y menos recursos. Sucede que una vez extraída la materia prima de los pozos petroleros y después de que se reservan en plantas colosales, se deben calentar a muy altas temperaturas para lograr su reacción. Y para acelerar este proceso se les agrega una dosis de catalizadores. Después de la expropiación de Lázaro Cárdenas, México estaba obligado a desarrollar métodos propios que no dependieran de una concesión extranjera para obtener productos derivados del petróleo a menor tiempo y menor costo. Samuel Gittler fue ingeniero civil, matemático y miembro del Colegio Nacional desde 1986. Gittler fue un hombre que llevó los números a niveles casi imposibles. Al igual que la de otros grandes científicos, una parte de su investigación lleva su nombre, los espectros Brown-Gittler. Para entender mejor estos espectros, hay que asomarse primero a la topología, pues es el tablero donde se juega esta ciencia. La topología estudia las propiedades cualitativas de los cuerpos geométricos y con la posibilidad de deformarlos sin problema, de manera que se puede obtener un círculo a partir de un triángulo para decir que estos dos son topológicamente equivalentes. La obra de Samuel Gittler dejó resultados teóricos que sirven en múltiples áreas como la química, la economía, en la capacidad de interpretar cálculos computacionales o en la robótica para resolver problemas de planeación motriz. Además, mantuvo altos estándares en la investigación matemática en México durante décadas y fue uno de los fundadores del Departamento de Matemáticas del Centro de Investigación y Estudios Avanzados del Instituto Politécnico Nacional, uno de los departamentos de matemáticas más importantes de América Latina.
Soy Diego Valadez, miembro del Colegio Nacional, donde tengo el privilegio de compartir la participación en esta formidable institución de la cultura mexicana con don Miguel León Portilla y con muchos otros eminentes protagonistas de la ciencia, del arte y de la cultura en general de México. Al rendir un homenaje al que me sumo gustoso a don Miguel León Portilla, estamos también reconociendo la trayectoria de un mexicano ejemplar que ha dedicado su vida al estudio de nuestra historia, pero además del pasado también se involucra en el presente, porque es un defensor de las culturas mexicanas, de la riqueza lingüística del país, de la exuberante producción que generaron las lenguas indígenas, y también es uno de los más fervorosos defensores de la propagación de los viejos valores de la filosofía mexicana, que junto con nuestra literatura tradicional forman uno de los acervos culturales más importantes de nuestro país.
¿Cómo ha contribuido Miguel León Portilla a la cultura de México? Yo creo que ha hecho él solo, desde sus posiciones políticas, culturales, filosóficas sobre los pueblos originarios, ha logrado él solo más que muchísimas políticas lingüísticas de gobierno. Miguel tiene una obra multidisciplinaria porque su visión de los pueblos es multicultural, como debe ser cualquier pueblo. Miguel ha insistido una y otra vez en que las lenguas son patrimonios intangibles de los seres humanos y que cuando se pierde una lengua, se pierde un patrimonio para la humanidad. También ha hecho Miguel algo que es una reflexión profundísima sobre cómo fue el contacto, el encontronazo de la conquista. Y Miguel encontró, cuando era embajador en la UNESCO, encontró un eufemismo buenísimo, hay que decirlo, que fue encuentro de dos mundos. Me parece que él su impulso desechó un término muy desafortunado para la cultura, que es el descubrimiento de América, y lo llamó con un acertadísimo eufemismo, políticamente muy, muy acertado, y puso las aguas un poquito en calma en el año 92, Encuentro de dos mundos. Miguel tiene obra trascendente y profundísima sobre cómo se dio este encuentro. Y además es un hombre altamente ejecutivo, o sea, si él te dice esto hay que hacerlo y lo vamos a hacer así, Miguel León Portilla lo hace así. O sea, no solamente está en este mundo filosófico, en el discurso defensor de los pueblos indígenas, sino está en la ejecución de cómo hacer más visibles y darles respeto. Yo creo que ha contribuido a quitar una cantidad gigante de estereotipos que caían y recaen, por desgracia, todavía en los pueblos indígenas.
Quisiera destacar un aspecto de la enorme obra de don Miguel León.
So in a few seconds we'll start this morning session, and it's my pleasure to present the first speaker, Mariano Álvarez from Buenos Aires and CONICET. And Mariano worked on Hochschild cohomology with mostly application to representation theory. And he will now speak about Hochschild cohomology and its algebraic structures. Thank you very much.
Okay. Okay. First, I'd like to thank the organizers for their invitation. It's been a really great conference so far. Let's hope we don't ruin it now. Okay, so what I'm going to talk about is Hochschild cohomology and its algebraic structure. So that's what I work on. So what I want to explain a bit is what is Hochschild cohomology, what's the algebraic structure we have in mind, and show you a few of the examples, things one can say about Hochschild cohomology and how we use it, and give a little example of the sort of thing one can do. Okay, so Hochschild cohomology started with that paper of Hochschild in which he defined Hochschild cohomology just saying cohomology, of course. And he actually says that the cohomology theory for associative algebras had been already constructed by Eilenberg and Steenrod, I think, but it was never published. So what is Hochschild cohomology? He gives a very, very concrete definition, which is slightly weird because at that time he had homological algebra. He knew the book by Cartan and Eilenberg, but he gives a very, very concrete construction. So he considers, I should say, all my algebras will be over a field, algebraically closed if we need it, and just to keep things simple. And algebras, not differential graded or anything, just associative algebras. So I have an algebra A, and an A by module M. So he considers the space of P multilinear maps from A to M. That's CPAM. And he constructs a complex like that. I'm going to describe the differentials. And by definition, the Hochschild cohomology of A with values in M is the homology of that complex. So let's just write down. So if you have never seen it, so you have an idea of what these things are. So a typical differential is this one. So going from degree 2 to degree 3 in the complex. So you start with a map, something here. So F is a bilinear map from A to M. And the differential, well, it's going to be a map from the tensor cube to M, and it's a very nice formula once you get to it's a very nice formula. It's the Hochschild coboundary. So this is just, you take F A B C times A minus F of A B C plus F of A B C minus F of A B C. So it's a formula. It's justified by the fact that it works, but, well, it doesn't really matter for us right now. So he constructs an explicit complex, and the cohomology of the algebra is that, the cohomology of that complex. Nowadays, we do things a bit differently. So the coefficients in this cohomology theory are bimodules. So we construct an auxiliary algebra, which is called the enveloping algebra, with just the tensor product of A and its opposite algebra. So the whole point of this thing is that the left modules over the enveloping algebra are the bimodules over A. So that's a nice category. And one can check that the Hochschild cohomology with values in M is isomorphic to the X functor evaluated in the category of A bimodules, so AE modules, evaluated at AM. Yeah, the proof is very simple. One constructs an explicit projective resolution of A in the category of A bimodules, P, such that when you apply the home factor to M to P, you get exactly Hochschild's complex. Yeah, so this is a proof by inspection. And this resolution P is called the bar resolution or the Hochschild resolution. And it has this shape. I'm not going to enter in details, but I just want to remark that this is big. So this is complex P dot, has in degree P this module. And this is very simple, it's nice. The nice thing about the Hochschild, the bar resolution is that we know it is there, and it's functorial and everything, so that's very useful. But it's almost useless to do anything else, because it's big. So imagine that A is finite dimensional, then this complex P grows exponentially with P. So that complicates things enormously. Okay, but the whole point of expressing cohomology as an X functor is that we know we can compute it using any resolution. Okay, so in practice, what we do is you have an algebra, you find a good, nice resolution that's adapted to it, which is never, in no case, it is the bar resolution, and you do something. And by now we have techniques to find good resolutions. If you know your algebra so that you have a good presentation, for example, then we know how to construct explicitly with maps and everything, a projective resolution which was essentially minimal in some way. So we know how to do this. It's a lot of work, but it works. And okay. So the modern definition of Hochschild cohomology, at least when we have a ground field as opposed to a commutative ring, is this one. So we define Hochschild cohomology nowadays as the X from A to M to an A bimodule M in the category of A bimodules. And X goes with Tor, so we define also Hochschild homology. That's not in Hochschild's paper. So this is Hochschild homology with coefficients in M, so this is just the Tor. Yes, and usually as a matter of notational, it's not much more convenient because the number of letters is the same, but when the bimodule is A, the regular bimodule, we usually write HHA instead of HAA. And same thing with homology. Okay, so what did Hochschild want to do with it? Yes, it was a time when people constructed cohomology theories. It was very in the spirit of the times, but you had to justify your cohomology theory with some applications. And in Hochschild's paper, there are three. His algebras are finite-dimensional algebras. He does not say so, but they are. And so the first application is an cohomological characterization of separability of an algebra. So an algebra is separable, which is, if you don't know what it is, it's the generalization to algebras of the definition of an separable field extension. So an algebra is separable if and only if H1 is 0. And then all the others are also 0. Because if you have the second application, which is expected at that time, people knew very well about group cohomology, so this is no surprise at that moment. So the second cohomology group classifies algebra extensions, and algebra extensions of A is simply a surjective map from another algebra B, but not all extensions, the singular ones, which are those whose kernel has square 0. Yeah, so that's H2 of group cohomology does the same thing. Here, of course, you have up to an equivalence relation and so on, but essentially H2 gives you extensions. And the main application in the paper is this theorem, is that every time you have an extension of a separable algebra, remember everything is finite dimensional, then you have a section. This is Wedderburn's principal theorem, but for separable algebras. Okay? So that theorem was quite a big thing at the time, and his proof is extremely nice. Okay? The other proofs of that theorem that they had at that moment were extremely computational, if you want. It's quite complicated. Okay? So that's what Hochschild wanted Hochschild cohomology for. So whenever one presents Hochschild cohomology, does this, the low degree part. So H0, it's very easy to check that it is the center of the algebra. So H1 is this thing. So if you have an algebra, you know what a derivation of A is. And it's just a linear map from A to A, which satisfies Leibniz rule. And in general, if you have a non-commutative algebra, you have some boring derivations. So if A is an algebra, and A, let's say M, is an element of A, then there is a map, which we can write add M, which is the map that you take an element A here, and so one can check that that is a derivation. And these are the boring ones. Yeah, they are there simply because our algebra in general is not commutative. Of course, if A is commutative, that map add M is 0. It's a commutator. Okay, so H1 sees the derivation modulo the boring ones, the ones that you know that had to be there, and we call that space, or that space is called the space of outer derivations of the algebra. If A is finite dimensional and over a algebraically closed field, this is the Lie algebra of the group, of the algebraic group of outer automorphisms of the algebra. And then, as we said before, H2 classifies singular extensions. So this is the cohomology in low degrees. It does what it should be in that way. Okay? So up to now, Hochschild cohomology is just a graded vector space. It's X of something. But the very important part of the cohomology theory is that it has an extremely rich algebraic structure on it. So the first part of it is the cup product. So as we said before, H0 of A is a ring. Yeah, and it turns out that the whole cohomology is a graded ring. Now, this is not surprising if you know homological algebra, because we define this thing as the XXIII algebra of A in the category of bimodules. So if you have an extension and another, then you can splice them, as Sarah Witherspoon described the other day, and that gives you a product. Of course, this is not extremely useful if you actually want to see the multiplication, because one never computes Hochschild cohomology as in terms of extensions. That would be impossible. So this is not very useful, but one of the key points about this product is that we know several ways to describe it. Yeah, so if we compute Hochschild cohomology using Hochschild's definition, so using these maps, these spaces of multilinear maps, so say you have a map of F in degree P, a G in degree Q, so these are multilinear maps of P and Q. So I'm going to describe a cup product, which will be in the P plus Q degree, and it's very simple. So this, you give it P plus Q elements in the algebra. You take the first P and give it to F. You give the last Q, give it to G, and you multiply. And it's very important that this multiplication here is in the algebra. Yes, when one defines the cup product for group cohomology, one does essentially the same thing, but this multiplication that appears here is in the field. And there is a difference. The field is commutative and the algebra is not. So that introduces complications. Okay, so again, this is not very useful because, as I said, one does not compute cohomology using the bar resolution either. Yeah, so one never computes Hochschild cohomology using these things. So even if this formula is extremely nice, it's something that one can compute, can work with. It's not computable in practice, so we need something else. But this is already in an exercise in Cartana and Eilenberg's book on homological algebra. It's very hidden, but you have to find it. But there is a way to compute the cup product in cohomology using any projective resolution. Yes, the point of expressing HH as a next is that we can vary the resolution, and we want to be able to do everything we do with cohomology using any resolution. And that's a problem, actually. So here it's easy. You start with a projective resolution, and you need an extra piece of information, which is a diagonal map. What is a diagonal map? It's something that's constructed as follows. So you have P, this is a projective resolution in the category of bimodules, so epsilon C augmentation. So you tensor it with itself. That gives you another complex, and here is a total complex. So A tensor A, of course, is isomorphic to A, so that composition is a complex over A, and it's easy to check that that's also a projective resolution of A. So basic homological algebra, you have the identity map down there, and you can lift it to a map of resolutions in a non-unique way, but any such map, delta, can be used to compute the product in cohomology. And in practice, this is doable. If you have an algebra and you were able to construct a projective resolution that was good enough for you to compute the cohomology, then this is a psychological statement, but it's very probable that you're going to be able to compute this delta and the product. Yes, that's something you have to experience. Okay. It's usually complicated. No one does this in public, but okay. Okay, so this gives a useful, workable definition of the product. It turns out there is something similar in homology. So if you hear, this proposition says that if you reverse the degree, so that homology is now in the negative part, it's just a technical thing, then this thing is a graded bimodule over the cohomology algebra. So that means that we have a left action and a right action, which we call the cap products, And, okay, so that's there. That's also computable using the diagonal map that I had before. Okay, so, but if we will go back to where we started this, H0 is the center, is not only a ring, but it's a commutative ring. Yes, so it turns out that the Hochschild cohomology is also commutative. This is rather surprising, essentially because of that observation I made that the cup product is defined using the multiplication of A, which can be very non-commutative, but it is commutative. So this is a non-trivial theorem. It's a very famous, I would say, theorem. And it turns out, this is not in Gerstenauer paper, but it follows from what he does, that the homology is now a symmetric graded module. Okay? So it was a bimodule with two actions, but actually the two differ only in a sign. Okay, so that's the theorem. This is an important theorem, so it has many proofs. Or the original proof by Gerstenhaber is very, very computational. It's annoying. It's the kind of thing that annoys you when you read it. And there are several levels of abstractions that you can put. Sarah mentioned a proof I wrote down in which one does not touch any elements. It happens in the abstract triangulated categories. But in fact, it turns out that the most useful proof of all is original one by Gerstenhaber, because in proving that commutativity, he found something else. The other proofs do not give you anything except the commutativity. His ugly computation gives you something else, which is a bracket. So, as we said before, H1 is this quotient of derivations by modulo the inner ones. That is a Lie algebra. Derivations are a Lie algebra with the operation of the usual commutator, and the denominator is an ideal. So that has a Lie algebra structure. And it turns out that the Hochschild cohomology, if you notice there, I shifted the degree so that what was H1 is now in degree 0. So now that is a graded Lie algebra. So this appears in the same paper. This is the same paper as before, and Gerstenhaber found this Lie structure in trying to prove the commutativity. Yes? So this is rather strange. I'm not going to explain how you could define it because it's long, but this is a very neat way of looking at what this bracket is. So you start with an algebra, A, so you can construct the derived category of the algebra. So that's a triangulated category, so you can look at the group of autoequivalences which respect the triangulated structure. That's called the derived Picard group. And you take the Lie algebra of that, and that's Hochschild cohomology endowed with its Gerstenhaber bracket. Of course, you have to make sense of everything I wrote down. So Bernard Keller wrote that very neatly, and that's a very nice description of what the bracket is, and it in particular shows that it's something very natural. Okay, so we know much less about the bracket than we know about the cup product. About the cup product, we don't know much, but for the bracket, we know even less. And the main problem here is that it's very difficult to compute. As I said before, if you can compute Hochschild cohomology, then you probably can also compute the bracket, the cup product, but usually describing explicitly the bracket is very difficult. And before 2016, there were alternative descriptions of the bracket, but they're completely useless from the point of view of computing. And the first new idea was in that paper by Chris Negron and Sarah Witherspoon, immediately followed by, or simultaneously, I don't know, by Yuri Volkov's paper with a similar idea, in which they provided your resolution, the resolution used to compute cohomology satisfies certain rather strict conditions, then they give you a procedure to compute the brackets which does not involve using the bar resolution, which is what you want to avoid very much. Okay, so that works, but with strong conditions on the resolution. Then I did something which, the bracket is something that's defined. You take an element in degree P and something in degree Q, and you bracket them and you get something. Well, in 2017, I gave a way of doing that, but when one of the factors has degree 1. It's a very special situation because in degree 1 you have derivations, but it actually turns out to be quite feasible. In practice, it's quite useful, and in many examples, knowing that small part of the cohomology is enough to reconstruct the whole thing of the bracket, because we also have the cup product, and the product and the bracket interact in useful ways, so that sometimes is enough, not always, of course. And then the most recent development is a paper by Yuri this year in which he extends the idea of Sarah, Chris Negron, and himself, and he removes all conditions on the resolution. I have not tried to use it in practice to compute with an actual algebra, but it's something that works. Okay, so at this point we have a lot of structure. So in Hochschild cohomology, we have this cup product, the bracket, and the whole package is called a Gerstenhaber algebra. The Gerstenhaber part, it means that encodes the relationship, the compatibility between the product and the bracket, which is here. So this is a biderivation for the cap product. So it's essentially like a Poisson algebra, but in which the Poisson bracket has degree -1. Okay, and then if you add in, you throw in the homology, then we have the cup, the bracket, and an extra piece of that, an extra map, which is called the condifferential here, something that goes from homology to homology, which I will ignore for now. And that whole thing is called a Tamarkin-Sigan calculus. And the thing is, this was defined in 2000, and this turns out to be what you need to do differential calculus on an algebra, whatever that means. Okay, so before going into that, let me finish up with this. So one of the, in general, why people want cohomology, because it's an invariant of an algebra, and they use it to tell things apart. People doing representation theory like to classify some class of algebras, and they usually consider two algebras, Morita equivalence is very boring, so the useful equivalence relation is derived equivalence. Two algebras are derived equivalent if they have the same triangulated equivalent derived categories. That means they have the same homological algebra, essentially. You want to consider two algebras the same if they have the same homological algebra. So there is a theorem, an important one, that says that if A and B are algebras which have the same derived category, then they have the same Hochschild cohomology. So the Hochschild cohomology only sees the derived category. This was proved originally by Happel and Ricard only at the level of algebras. So they showed that there is an isomorphism of algebras, and later Keller proved that the isomorphism respects the Lie structure. With his theorem, which describes the bracket as the Lie algebra of the group of derived Picard, then this is essentially obvious, but the original proof was before that. Okay, so, and in fact, we have more structure. As I mentioned before, we have this Sigan calculus, which includes the homology and the cap and the both products and the condifferential, and the whole thing is invariant under derived equivalence. And this was proved last year by Marco Armenta and Bernard Keller, and this year, Pedro Tamarov showed that, in fact, a stronger statement that if A and B are homotopy equivalent, then they have the same Tamarkin, which is a stronger statement. That makes sense if A and B are differential graded algebras and my algebras are not, but that's an important result. Okay, so as we've seen that this thing has a rich algebraic structure, but we only see the beginning of it. So in 93, Deligne conjectured or asked or wished that he said, I want the complex, the Hochschild complex, the one that Hochschild used, to be an algebra over the little disk operands. If you don't know what that is, it doesn't matter. That means that there should be lots of operations naturally defined on the Hochschild complex that interact in nice ways, encoded by a geometric object, which are little disks. I'm not going to tell you what that is, but I'm going to give you some consequences. So this was proved after partial results by Tamarkin in 1988, and since this is a very important theorem, it was then reproved many times. As you see, McClure and Smith gave 3 different proofs of this result. So this is actually, of course, they each proved slightly different things and more precise and more geometric, less geometric, but okay. So why this is good for us? Because this implies there is a general technology that says that if you have something on which the little disk operator acts, then it gets automatically lots of operations in the homology. So in this case, what happens is that if you have a space, then you can do the loop space, which is a space of loops, and then you can iterate it. So you get the double loop space. And it's been known by topologists for a long time that such spaces which are double loop spaces, their cohomology has a very rich structure. Not only they have the cap product and the Stingrod operations and the Adams operations, but they have lots of extra structure naturally. And all that comes from the action of this operand, and since Hochschild cohomology has that action, then we have all those operations also on cohomology. I don't think anyone ever bothered to compute because it's probably very, very difficult, but that shows that H8 is an extremely rigid object. Okay? So that should be useful. Okay? That's one of the reasons this is important. Okay, so let me give you examples to show you what is Hochschild homology in concrete cases. So the first real computation, and probably the first computation in Hochschild homology is this theorem by Hochschild, Constant, and Rosenberg. It's a very famous theorem that says, it's the first part. So if A is a commutative algebra, essentially of finite type, that means it is a localization of a finitely generated algebra over a field, and smooth, which means that if you view A as an algebraic variety, then it's smooth. Then there are isomorphisms. The easier one is this one. So Hochschild homology of such an algebra is this omega here is the module of Keller differentials. So this is differential forms. And this is the exterior algebra on omega. So for these algebras, homology gives you the RAM complex, essentially, the algebraic RAM complex. And for cohomology, what you get is this. So there was the derivations as before. And this is the exterior algebra on the module of derivations of the algebra. That's called the algebra of polyvector fields. Yes, and of course, at that time, they did not have the calculus or anything, but one can actually enrich this theorem so that it says that if the whole structure, the cap product, the other product, the bracket, and everything is what one would expect in a situation in which you have forms and vector fields. See? Derivations are the algebraic counterpart of vector fields. And the second version of the theorem is if you take A equal the C infinity functions on a smooth compact manifold, then the same thing works. Now you have to interpret this as vector fields on the manifold, and omega as the omega, the first thing. And that's the usual calculus. That's why these things, this structure that we called a calculus before is called a calculus, because when A is the functions on a manifold, then you can actually do calculus. And one of this explains one of the reasons people like Hochschild homology. It gives you a way to do calculus in non-commutative situations. If you want to do non-commutative differential geometry, then Hochschild homology is your thing. Well, one of them. Okay, so let's give an example in the other direction. So this is this is an important example because it's the only one compute by hand. So take a field for simplicity in which 2 is not 0 and consider this algebra. So this small algebra, dimension 2. And well, one can compute, this is an exercise, a long one, but it works, that the cohomology is this algebra. This is generated in degree 1, h, y, and z. In degree, the red numbers are the degrees, and they have certain relations. And then you can compute the Lie brackets, and you come up with that, and there is another one which is 0. Those are the non-zero brackets in the generators. Okay, so this is CC. As soon as you change this polynomial x squared for something more complicated, or in fact for any polynomial, it becomes more complicated to the computation. This computation had been done much before in homology, which is slightly easier, and not as an algebra, because the homology is not an algebra. But the first time this was done in general, more or less, was by Thorsten Holm in 2000, and he described the algebra structure. And then I did the bracket, which is, at that time, we did not know how to compute brackets using anything but the original definition, so it was very complicated, but it worked. And these algebras are complete intersections. So after some time, Buchweiz and Roberts realized in what way the complete intersection condition, what role played in the proof, and they managed to generalize this, which I'm not going to give you the final result because it's complicated, but they were able to compute Hochschild homology as a Gerstenhaber bracket, so a Gerstenhaber algebra, the cap product and the bracket. Okay? So this is my favorite example. So all these examples that I mentioned before are commutative. So it's commutative algebra. This is a non-commutative one. So you take X and a smooth affine algebraic variety, complex numbers for simplicity, and then there is a well agreed upon definition of what a differential operator on such a thing is, due to Grothendieck, and you consider the algebra of differential operators, and you compute Hochschild cohomology. Now, it's a non-commutative algebra, and it turns out that the Hochschild cohomology of differential operators is the de Rham cohomology of the underlying variety. So, Hochschild cohomology, if you compare it with HKR, if you do Hochschild cohomology of functions, you get differential forms. If you do Hochschild cohomology of differential operators, you get the de Rham cohomology. It's like you skip a step. Yeah? So this is a really nice theorem. This was proved originally by Mariusz Wojcicki and then by Brylinski, essentially different ideas. And nowadays we understand this as a quantization result, because the differential operators on a manifold can be viewed as a quantization deformation of the algebra of functions on the cotangent bundle of the manifold. So you need a lot of technology, but from that observation you can reprove this. This is a nice theorem, but of course it works for smooth things. What happens if X is not smooth? Then a very nice example is this one. So take an affine curve, a complex affine curve, and suppose such a thing has a normalization, something which coincides with the desingularization of the manifold of the curve actually, and there is a natural map going from X tilde to X, which is called the normalization map. If that map is injective, then, well, you can define differential operators on the singular curve. You construct the algebra, compute cohomology, and what you get is the de Rham cohomology, but of the thing above. Well, that's one thing that happens in Hochschild cohomology. It sees something that you don't really have. Yes? Okay, so this is not really proved in the paper by Smith and Stafford. They actually, what they do is they study the algebras of differential operators on the two curves, and they show their Morita equivalent. In particular, the derived equivalent, and as we showed before, then they have the same Hochschild cohomology, and then everything follows. So this is a nice theorem, and this is a more singular kind of example. So take G, a finite group, V, a representation, a complex representation of G, then you can construct V modulo G. That's usually a very singular variety. It's very, very rare that the quotient is smooth. It's only when G is generated by reflections. And okay, so you have this singular variety, you construct the algebra of differential operators on that thing, and then you compute Hochschild cohomology, and then, well, this looks hopeless, but actually it's quite magical. You can actually compute that, and it turns out that you take the center of the group algebra of the group, then there is a natural filtration on that algebra in the center, which is determined by the representation V, and you take the graded associated algebra, and you get an isomorphism of algebras there. You know, this was proved by Alev, Farinati, Thierry Lambre, Andrea Solotar for the linear part, and then I proved that the isomorphism is an isomorphism of algebras. And at the same time, Eric Vassereau showed the following. If you take the Hilbert, so C2 is the complex plane, which is not the plane, this is confusing, but this is a two-dimensional affine space over the complex numbers, and this is the Hilbert variety on that. The Hilbert scheme of points, of n points. Essentially, it is the set of all configurations, unordered configurations of points in the plane, but which may collapse in some way. It's a complicated variety, and he computed that the de Rham cohomology of that thing, which is very important, is exactly the same thing as we did as an algebra. And nowadays, we know how to prove the equivalence from one to the other using formality. Kontsevich results on formality, but this is again a situation in which, so you start with V over G, that's a singular thing, so you can consider a desingularization. In this case, it happens to be this scheme, so there is a natural map. And what you really want is this one, the geometric information about the desingularization, the Hilbert scheme, but Hochschild cohomology allows you to do things below, which is much, much simpler. Yeah, so that's nice. Okay, so this is, in this, if you look, all my examples come from geometry and involve differential operators, because those are my favorite algebras. But, okay, so here we have A a complex arrangement of hyperplanes. So it's a finite set of hyperplanes in a complex vector space. Central, I should have said. They are linear hyperplanes. So that's an interesting thing from many points of view. And some of those arrangements are called free. So on Monday, Claudia defined what, if you have a curve in the plane, for instance, she defined what the Lie algebra of derivations that preserve the curve are. So they're essentially tangent derivations. And one says that a curve is free if that module of derivations is free. So it's most curves are not free, but those that are very interesting. So this is the same thing. So you have an arrangement. So this is a divisor in a complex affine space. You consider the module of all derivations that preserve the arrangement, the subvariety, and you say that the arrangement is free if that module is free as a module over the functions. So most arrangements are not free, but free arrangements are important. For example, if you like Lie theory, then you like Cartan algebras, and in the Cartan algebras you find root systems, and if to each root you put the orthogonal plane, then you get a configuration of planes in a vector space, and it was proved by Terao, I think, or Saito, someone, that that arrangement is free. So if the hyperplanes for the Lie algebra are free, then free arrangements must be important. So what we did here was, instead of only considering, as Claudia did, the derivations that preserve the subvariety, we consider the whole algebra of differential operators that preserve it. This is what we call the algebra of differential operators tangent to the arrangement. And then this is a complicated thing, but you can compute Hochschild cohomology of that, and it turns out that inside of that, as an algebra, we compute this as a Gerstenhaber algebra, but inside that there is a copy of the cohomology of the complement of the arrangement, which is a very important invariant of the arrangement. So a lot of effort has been put into computing this thing. So here what is interesting is that this is not the same thing, they are not isomorphic, but we essentially understand what is the difference. So it's complicated to explain, but it can be done. So this was done in Francisco Cordon's thesis this year. Last year. Okay, so if you see this is a pattern, you start with a geometric object, you attach generally a non-commutative algebra to it, then the Hochschild cohomology of that gives you something about the geometric situation you started with. And it becomes enriched with, here you get the RAM cohomology is an algebra. So here you get the whole structure. And the nice thing is that in this way you relate your geometrical problem to representation theoretic problems of the algebra, which usually is good. And in all these examples that I gave, why do we do this? Because, well, for instance, here in this case, we wanted to compute the automorphism group of the algebra. And that's usually extremely complicated. You need something to do to start that work, and we were able to do that, and the argument really depends on knowing the Hochschild cohomology. So it's an useful invariant. I'm not showing you what we use the cohomology for, I'm just showing you what the end result is, but trust me, it's useful. Okay. So this is a similar line of examples, a completely different line of examples, but with the same objective. You start with a situation, and you use Hochschild cohomology to construct an invariant that you wanted, and you produce it in a rather systematic way. The good thing is that this gives you a systematic way to obtain interesting things. Yes? In each case, we show that cohomology is something interesting before cohomology. Okay, so this is representation theory, so you have a quiver. So you have a finite quiver Q, you take an admissible ideal, and you consider the algebra associated to that. So Q is a graph, and we say, or one says, that A is gentle if the following three conditions are satisfied. The first one is that Q, the graph, is not very complicated, at each vertex, there is at most 2 arrows coming out, and at most 2 arrows coming in. So it's locally simple. Second, the relations that generate my ideal is, so K of Q, if you don't know, is as a vector space, it's the path algebra, has a basis, as a basis the set of paths in the graph that we have. So an I will be generated by paths of length 2. So I pick some subset of paths of length 2 in my quiver, and my algebra A is as a vector space, is the set of paths that do not contain any of the subpaths that I picked of length 2. So this is my I, and there is a condition on gentleness, which is always annoying to explain, but essentially it says something like this. So suppose you start in a vertex in the graph, and you move along an arrow, then arrows are never 0 in the algebra because that's in the admissibility condition, but then you wonder if you can continue your path along the graph having a non-zero path. And gentleness means that there is only one option. Once you decided in which direction you want to go, then you have no more choices along the way. Until you are blocked. And that's half of the condition, and the other part is that also holds for 0 paths, which is different. It's hard to explain, but suppose that's. So I say that a path is saturated. For instance, this path will be saturated if all its factors of length 2 are in my ideal. So it's a path that is 0, but very much so. Not only for one reason, but for all the possible reasons. So gentleness means that if you want to go along a path of a non-zero path, you do not have options, and if you want to go along saturated paths, then you also do not have any options. This is a complicated set of conditions, but it's actually quite natural, and they were introduced by Ibrahim Assem and Skowronski some time ago. These algebras are very well known. They are, in particular, those conditions imply that it is a special biserial algebra or a string algebra. It falls in many well-studied families of algebras, and in particular, we know their complete representation theory due to work by Ringel and many others. Okay? And I should say, Sibylle Schroll is going to talk about that. You're going to learn why this appears everywhere, but it appears in representation theory, cluster theory, physics, and so on. It's a very nice class of algebras that has the nice property that is closed under derived equivalences. If you have 2 algebras, one of them is gentle, and the 2 are derived equivalent, then the other one is also gentle. That's very nice. Okay, so a few years ago, Shadira Valdivieso Diaz showed that if A, here is the Jacobian algebra corresponding to a puncture triangulated surface. I'm not going to explain to you what that is, but you start with a surface with a triangulation, and there is a certain way of producing an algebra from that, and that algebra is always gentle. And she computed the Hochschild cohomology of those algebras, which are gentle algebras, and in terms of some invariants, which were defined by Avella-Minos and Guys. And so she observed that the Hochschild cohomology of such algebras can be computed in terms of these certain numbers that I'm not going to explain because it's too long. But the nice thing is that Avella-Minos and Guys showed that these numbers, these invariants, are derived invariants. So if you take 2 gentle algebras, you compute it, and if the 2 are derived equivalent, then they are the same. This is important because people really want to classify gentle algebras up to derived equivalence, and it's difficult, so having an invariant is useful. And what is annoying is that the proof of invariance is very complicated. So you start with the algebra A, you construct what is called the repetitive algebra, which is an infinite-dimensional, non-unitary, self-injective, huge thing. And then with that thing, since it's self-injective, you can construct what is called the stable representation category. These are modulo injectives, essentially. And okay, so people in representation theory spend a century trying to understand this thing, and they do it very well. So you can compute what is called the Auslander-Reiten quiver of that thing. And we know this very, very well. And what these people do is they show that these invariants actually count something special things in that quiver. So, and since that quiver is obviously derived invariant, everything is derived invariant. And so that's it. So this is a rather, if you look at their paper, it's not very complicated, but it's not complicated because it depends on a huge amount of miracles. For instance, the existence of Ringel that described all the modules. So, okay, then what we're doing now with Andrea Solotar, Cristian Chaparro, Sibylle Schroll is trying to do that in general. So we are So we started with a gentle algebra in general, not coming from a surface now, and well, they all come from a gentle algebra. So we compute the whole structure. We already know very well how to describe the cup product and the Gersten-Haber bracket. So we have a Gersten-Haber algebra that's completely understood. And then it turns out that using the algebraic structure of cohomology, so HH dot is an algebra, so you can do this. This HH plus is the positive degree part. So here you have H plus times H plus. So that's the subspace generated by things that are non-trivial products, essentially. And you can do the quotient. This is a graded vector space. And you can count the dimensions of that in each degree. And those dimensions correspond to some of the AAG invariants. Yeah, so, and they say you can do the same thing for the bracket. You take H modulo the space of things that are brackets in a non-trivial way. And that also gives you a graded vector space. You compute the Hilbert series of that. And those numbers are not, we don't get all of them, but we get some of these AAG invariants. And what's the point of this is that now it is obvious that these numbers are derived invariant. Because HH, the cohomology, the product, and everything in this recipe to compute them is derived invariant. So now it's automatic. One can do some things. This gives some of the AAG invariants. If you do this using the homology and the cup product now, then you get some other of the invariants, and we think that we can compute the whole set of invariants by similar tricks. You have to vary coefficients, essentially. And the last thing I want to say is, what's important? Okay, I forgot my last observation, but I just end here. That's what I want to say.
So
I have something I want to say.
We'll thank the speaker. And are there any questions? Yes, I have a question. You mentioned the fact, Lalín conjecture,
yes,
about the fact that the Hochschild complex has a structure of algebra over the little disk operad, and you say this generates new operations. Do you mean that these operations are secondary operations? Means not well defined up to something?
They're like Dyer-Lashow operations, that sort of thing. There's a whole hierarchy of operations. The first one is the cup product, which comes from the action in degree 2, and the bracket comes from compatibility between the 1 and degree 2, and then you get higher things that are braces, and most of those operations had to be found before, because one thing that one should, these maps that we have when we compute Hochschild cohomology using the Hochschild complex, you can picture them like this. You start with P things in A, and you somehow mix them, and you produce another one. So that's a graphical way of drawing what a cocycle is, and these things can be composed. If you have, for instance, 2 of these and something like this. So if you have several of these cocycles, you can compose in many ways. That's how the little disks get into, because it's exactly the same idea. And, well, the problem is how to get something that works up to homology that's not trivial, and that's where the geometry comes. But they're not secondary. They are
Well defined.
Well defined, yes. Yeah.
Okay, because in usual homotopy theory, the secondary operations are defined when some brackets are zero and things like that.
No, these are really well defined. Yes, sir.
Yeah.
So I have a follow-up question to this. These new operations, can one deduce that they're derived invariant?
No.
And if so, could they be a complete invariant then?
I doubt that. But, the problem is that the proofs are really complicated. And the way one constructs the action of the operator on cohomology to produce this is not very direct. It's not that you have a formula, it's you show that they exist in some way. It's done by doing homotopy theory in the category of operands. And so you show that essentially the original idea by Tamarkin and others is that you try to construct the action step by step, and you show that there is an obstruction theory, like in topology. You compute whatever is the obstruction and you find that it's zero, but you don't really make explicit anything. So it's not very helpful. I don't think anyone has computed any example.
Are there more questions? If not, I have another question. Okay. I'm sorry. Could you tell us a little bit more about your theorem comparing the Hochschild cohomology and the cohomology of the arrangement of hyperplanes, yes, when the arrangement of hyperplane is so-called free?
Free.
Because you say that it's included, but you don't, yes, say what is.
So this is this theorem?
Exactly, yes.
This thing, say,
so the right side is well known.
This is well known, so that's you have clear. A presentation and everything.
Yeah,
and what happens here is that here there is an element in degree 2, mm-hmm, which is together with the rest generates everything. Mm. And that element is actually very interesting because, if you have the arrangement, then the arrangement is a divisor, so you have a polynomial, and that polynomial has a Bernstein polynomial. Mm. So essentially the difference from here to here is encoding the Bernstein polynomial of the arrangement. Mm. For example, if the arrangement is free, then there is a theorem that says that the Bernstein polynomial is symmetric. Mm. Yeah? And this algebra diff of A is Calabi-Yau. Mm. So Hochschild cohomology is essentially symmetric, and it's the same observation. Mm. So I don't know how to describe what's rest, because it's not like it's generated freely over the cohomology of the complement by that element, but together they generate everything. Mm. I don't know a presentation. Mm. No, I'm working on that actually.
Okay.
Yes.
Now you have the last chance to ask a question. So if you miss this chance, this will be now too late, and we will thank the speaker again. And we will resume at 10:30 after coffee break.
Y me impresionó cuando, siendo muy chico, estando en el bachillerato, leí La visión de los vencidos, y es una obra epopéyica, absolutamente comparable a la Ilíada, una de las grandes tragedias de la historia de la humanidad. Pero probablemente el aspecto que a mí me conmueve más de don Miguel, aparte de tener la suerte de muchas veces sentarme a su lado y de sentirme un amigo de él, es el hecho de que para León Portilla los indígenas no son solamente parte de ese pasado excepcional que tuvimos, capaz de hacer pirámides o estatuas y piezas de jade y obsidiana, sino que para don Miguel León Portilla también los indígenas son ese grupo enorme de mexicanos que hemos marginado, que tienen una riqueza extraordinaria en términos culturales, en términos de conocimiento del ambiente, en términos lingüísticos, y para él no son solamente un vestigio del pasado, sino una realidad viva de México. Yo creo que uno de los grandes regalos que a mí me ha hecho el Colegio Nacional es la posibilidad de conocer y tratar a don Miguel y de haber recibido de mano suya la visión de los vencidos en náhuatl, que me parece la mejor demostración del compromiso de la cultura mexicana contemporánea con nuestro pasado y con ese otro componente del México que él se ha encargado de recuperar y llevar hacia la línea de primera.
Hola, soy Mardonio Caraballo, soy escritor, escribo en náhuatl y en castellano, en Ixtlapaloa, Nochi Noixnimen, Nopatlentle Machtiani, tocan Miguel León Portilla. Hola, ¿cómo están? Bueno, envío un saludo al maestro Miguel León Portilla. Pienso que la obra del maestro ha sido fundamental para entender a México, sobre todo desde sus personas y sus habitantes anteriores, los que llegaron primero, como dirían los zapatistas, ¿no? Pienso que es fundamental su entendimiento para con aquellos hombres y mujeres de los cuales nos había contado una versión que en algún sentido dignificara, a su vez que acusara todo lo que había ocurrido en un tiempo. Creo que es importante, es un hombre de su tiempo, si bien pienso que la gran contribución de Miguel León Portilla sobrevive al tiempo, también pienso que ha acuñado de cuya agua han abrevado múltiples artistas, múltiples escritores, ahora en lenguas originarias, que sin duda están haciendo una revolución con respecto de quiénes son, con respecto de la identidad, con respecto de México, quiénes somos los mexicanos, por qué somos como somos y por qué nos vemos como nos vemos. Y pienso que todas esas reflexiones no podrían haberse dado si no hubiese un inicio, y pienso que en ese sentido, en la historia, para entender la historia que tenemos ahora, para comprender a los pueblos indígenas en la narrativa nacional, me parece fundamental el agua, digamos, el abrevadero que se llama Miguel León Portilla.
Hola, ¿qué tal? Soy Juan Villoro, escritor y periodista, y me da mucho gusto poder hacer una evocación de Miguel León Portilla, uno de los grandes intelectuales de México, que ha sido un intercesor extraordinario entre la cultura y la lengua de los pueblos originarios, principalmente del náhuatl, y nosotros. Miguel León Portilla ha sido ese intermediario esencial entre un mundo desaparecido, derrotado, de los primeros mexicanos, que es el mundo de la visión de los vencidos, pero que todavía perdura entre nosotros, perdura sin una voz propia que se escuche, y que gracias a intercesores como Miguel León Portilla puede ser reconocido. Entonces ha sido valiosísimo este trabajo de entender la importancia, el significado del legado indígena. Ahora bien, creo que el gran legado de León Portilla tiene que ver con el pasado, pero también con el futuro. Él apunta a una cultura que ha sido sojuzgada, destruida, pero que puede ser todavía rescatada y puede perdurar entre nosotros, pero creo que implícitamente también está señalando a un futuro. ¿Cómo seremos los mexicanos del porvenir? Y yo creo que ahí esta figura puente nos está diciendo la verdadera historia de los pueblos originarios será escrita en su lengua o en sus muchas lenguas y será escrita por ellos mismos. Llegará un momento en que México no tendrá necesidad de intermediarios, de intercesores para conocer esa cultura, porque esa cultura volverá a estar viva entre nosotros. De modo que creo que el gran legado de Miguel León Portilla tiene que ver con la recuperación de un pasado, pero también con el señalamiento de que hay una aventura por venir, que es la de que los propios pueblos escriban su historia en la lengua que él ha traído hasta nosotros.
Marcos Moszyński-Borodiański fue físico y miembro del Colegio Nacional desde 1972. Moszyński continuó su labor en la UNAM con la búsqueda de las propiedades del oscilador armónico. Un sistema físico tiene simetría porque después de transformarse queda invariante. Por ejemplo, después de que una esfera gira sobre alguno de sus ejes, su forma es exactamente igual antes y después de la rotación. Este concepto fue aplicado por Moszyński para explicar las estructuras del núcleo atómico en un oscilador armónico. ¿Y qué es un oscilador armónico? El oscilador se asemeja al comportamiento de un resorte que cuando se le intenta estirar, tiende a regresar a su estado normal y comienza a oscilar. Moszyński logró simplificar los cálculos en estructura nuclear usando los que él llamó paréntesis de transformación. Sus estudios llegaron a tal fama que la comunidad científica se refería a ellos como los Moszyński brackets. Moszyński no solo se convirtió en referencia mundial, sino que ha dejado un legado en las ciencias exactas. Ahora, como homenaje a su carrera científica, la Fundación Marcos Moszyński continúa con sus ideales otorgando las cátedras que llevan su nombre. Este es un programa anual que impulsa la trayectoria y proyectos de investigación de jóvenes científicos mexicanos en las áreas de física, matemáticas y las ciencias químico-biológicas.
Pues estamos aquí, Mardonio Carballo y yo, para convidarlos al Colegio Nacional y también a este museo a un diálogo de experiencias compartidas. Los pueblos originarios, Mardonio, como tú sabes muy bien, consideran que los hombres de cierta edad, las mujeres de cierta edad, son personas de juicio, son personas cargadas de experiencia, y a ti se te ocurrió recoger esto para que dialoguen en distintas disciplinas personas que son decanos de su profesión con los que empiezan esa misma trayectoria de vida.
Sí, la gran maravilla, ¿no? La gran maravilla de tener también jóvenes expertos en temas diversos que de alguna forma importan pues en general al público, ¿no? A la vida, ¿no? Hablar de la vida a través del tiempo, hablar de la experiencia, hablar de la sapiencia también, ¿no? Que da la posibilidad de llegar a ciertas edades ejerciendo ciertas profesiones, ¿no?
Vamos a estar en diálogos los viernes hasta que acabe el año, prácticamente hasta el 13 de diciembre, y vamos a arrancar el próximo viernes 2 con un tema muy importante: identidad, pueblos, política, comunidades originarias de México. Vamos a seguir con el exilio español en México, un decano del exilio español hablando con una descendiente del exilio español. Seguiremos con un tema muy importante: salud, medicina, enfermedad, y así vamos a continuar con algunos de los temas más significativos de nuestro tiempo, contando con expertos ya muy probados, pero también con jóvenes que muy pronto serán expertos.
Sí, y qué maravilla que podamos tener un evento así. Esto es en colaboración con la Dirección General de Culturas Populares de la Secretaría de Cultura y el Colegio Nacional, ¿no, Juan?
Los viernes a las 7 de la noche, ahí en Donceles 104, Centro Histórico, los esperamos en el arranque del ciclo.
Juego, diálogos a través del tiempo.
Alejandro Frank es físico y se integró al Colegio Nacional en el 2016. Frank ha desarrollado trabajos en la mecánica cuántica y es pionero y fundador en la teoría algebraica de la dispersión. Para Alejandro, la dispersión algebraica es una metodología matemática para describir la interacción entre las partículas. En mecánica cuántica hay un principio que no permite saber con qué velocidad se está moviendo un sistema, pero sí saber dónde está, o al revés, saber su velocidad, pero no su ubicación. Pero Frank desarrolló un método para saber ambos, la velocidad y la posición. Lo logró analizando un sistema en su transición de fase. Para este tipo de análisis se necesitan modelos teóricos muy complejos. Frank describe a la mecánica cuántica como una técnica matemática especialmente capaz de describir a la naturaleza. Y sus investigaciones sobre la teoría algebraica de la dispersión las aplicó en este campo. Octavio Novaro Peñalosa fue físico y miembro del Colegio Nacional desde 1995. Una de las ramas que más le debe a Novaro es la industria petroquímica por sus estudios sobre fuerzas intermoleculares y catálisis teórica. Los catalizadores son partículas muy pequeñas de metales preciosos y Novaro los describía como piedras más pequeñas que las aspirinas con el poder de acelerar las interacciones entre las moléculas del hidrocarburo. Y el resultado era genial, reacciones químicas en menor tiempo, lo que implicaba usar menos energía y menos recursos. Sucede que una vez extraída la materia prima de los pozos petroleros y después de que se reservan en plantas colosales, se deben calentar a muy altas temperaturas para lograr su reacción. Y para acelerar este proceso se les agrega una dosis de catalizadores. Después de la expropiación de Lázaro Cárdenas, México estaba obligado a desarrollar métodos propios que no dependieran de una concesión extranjera para obtener productos derivados del petróleo a menor tiempo y menor costo. Samuel Gittler fue ingeniero civil, matemático y miembro del Colegio Nacional desde 1986. Gittler fue un hombre que llevó los números a niveles casi imposibles. Al igual que la de otros grandes científicos, una parte de su investigación lleva su nombre, los espectros Brown-Gittler. Para entender mejor estos espectros, hay que asomarse primero a la topología, pues es el tablero donde se juega esta ciencia. La topología estudia las propiedades cualitativas de los cuerpos geométricos y con la posibilidad de deformarlos sin problema, de manera que se puede obtener un círculo a partir de un triángulo para decir que estos dos son topológicamente equivalentes. La obra de Samuel Gittler dejó resultados teóricos que sirven en múltiples áreas como la química, la economía, en la capacidad de interpretar cálculos computacionales o en la robótica para resolver problemas de planeación motriz. Además, mantuvo altos estándares en la investigación matemática en México durante décadas y fue uno de los fundadores del Departamento de Matemáticas del Centro de Investigación y Estudios Avanzados del Instituto Politécnico Nacional, uno de los departamentos de matemáticas más importantes de América Latina.
Soy Diego Valadez, miembro del Colegio Nacional, donde tengo el privilegio de compartir la participación en esta formidable institución de la cultura mexicana con don Miguel León Portilla y con muchos otros eminentes protagonistas de la ciencia, del arte y de la cultura en general de México. Al rendir un homenaje al que me sumo gustoso, a don Miguel León Portilla, estamos también reconociendo la trayectoria de un mexicano ejemplar que ha dedicado su vida al estudio de nuestra historia, pero además del pasado, también se involucra en el presente, porque es un defensor de las culturas mexicanas, de la riqueza lingüística del país, de la exuberante producción que generaron las lenguas indígenas, y también es uno de los más fervorosos defensores de la propagación de los viejos valores de la filosofía mexicana, que junto con nuestra literatura tradicional forman uno de los acervos culturales más importantes de nuestro país.
¿Cómo ha contribuido Miguel León Portilla a la cultura de México? Yo creo que ha hecho él solo, desde sus posiciones políticas, culturales, filosóficas sobre los pueblos originarios, ha logrado él solo más que muchísimas políticas lingüísticas de gobierno. Miguel tiene una obra multidisciplinaria porque su visión de los pueblos es multicultural, como debe ser cualquier pueblo. Miguel ha insistido una y otra vez en que las lenguas son patrimonios intangibles de los seres humanos y que cuando se pierde una lengua, se pierde un patrimonio para la humanidad. También ha hecho Miguel algo que es una reflexión profundísima sobre cómo fue el contacto, el encontronazo de la conquista. Y Miguel encontró, cuando era embajador en la UNESCO, encontró un eufemismo buenísimo, hay que decirlo, que fue encuentro de dos mundos. Me parece que él su impulso desechó un término muy desafortunado para la cultura, que es el descubrimiento de América, y lo llamó con un acertadísimo eufemismo, políticamente muy, muy acertado, y puso las aguas un poquito en calma en el año 92, Encuentro de dos mundos. Miguel tiene obra trascendente y profundísima sobre cómo se dio este encuentro. Y además es un hombre altamente ejecutivo, o sea, si él te dice esto hay que hacerlo y lo vamos a hacer así, Miguel León Portilla lo hace así. O sea, no solamente está en este mundo filosófico, en el discurso defensor de los pueblos indígenas, sino está en la ejecución de cómo hacer más visibles y darles respeto. Yo creo que ha contribuido a quitar una cantidad gigante de estereotipos que caían y recaen, por desgracia, todavía en los pueblos indígenas.
Quisiera destacar un aspecto de la enorme obra de don Miguel León Portilla, que es la que se relaciona con su defensa de los pueblos amerindios y de sus lenguas. Al paso de los años, don Miguel se ha convertido, diría yo, en el principal portavoz de la lucha de los pueblos amerindios y también de muchos lingüistas como yo, porque se respete la dignidad de estos pueblos, se respeten sus costumbres y se respeten sus lenguas. En ese sentido, el papel de don Miguel es invaluable. Donde quiera que uno se interese por saber qué hacer en favor de nuestras lenguas amerindias, siempre va a tener uno que consultar lo que ha escrito don Miguel León Portilla e incluso su actividad permanente. Quizás ahora no por su salud delicada, pero todos lo hemos visto participar activamente en esta promoción de los pueblos y de sus lenguas. Yo creo que es uno de los aspectos de don Miguel que van más allá del filólogo y el historiador que es, a un compromiso con nuestros pueblos amerindios.
Para mí y para todos los mexicanos, don Miguel León Portilla debe representar el mejor ejemplo de lo que es un hombre de cultura, un hombre que aprendió tanto como pudo de su entorno, que recogió la cultura pasada y presente de los mexicanos y que nos está dejando una herencia cultural absolutamente extraordinaria. A mí me impresionó cuando, siendo muy chico, estando en el bachillerato, leí La visión de los vencidos, y es una obra epopéyica absolutamente comparable a la Ilíada, una de las grandes tragedias de la historia de la humanidad. Pero probablemente el aspecto que a mí me conmueve más de don Miguel, aparte de tener la suerte de muchas veces sentarme a su lado y de sentirme un amigo de él, es el hecho de que para León Portilla los indígenas no son solamente parte de ese pasado excepcional que tuvimos, capaz de hacer pirámides o estatuas y piezas de jade y obsidiana, sino que para don Miguel León Portilla también los indígenas son ese grupo enorme de mexicanos que hemos marginado, que tienen una riqueza extraordinaria en términos culturales, en términos de conocimiento del ambiente, en términos lingüísticos, y para él no son solamente un vestigio del pasado, sino una realidad viva de México. Yo creo que uno de los grandes regalos que a mí me ha hecho el Colegio Nacional es la posibilidad de conocer y tratar a don Miguel y de haber recibido de mano suya La visión de los vencidos en náhuatl, que me parece la mejor demostración del compromiso de la cultura mexicana contemporánea con nuestro pasado y con ese otro componente del México que él se ha encargado de recuperar y llevar hacia la línea de primera.
Hola, soy Mariano Suárez, soy escritor, escribo en náhuatl y en castellano, en Ixtlapaloa, nochi noixnimen, nopatle tlemachistiani, tocan Miguel León Portilla. Hola, ¿cómo están? Bueno, envío un saludo al maestro Miguel León Portilla. Pienso que la obra del maestro ha sido fundamental para entender a México, sobre todo desde sus personas y sus habitantes anteriores, los que llegaron primero, como dirían los zapatistas, ¿no? Pienso que es fundamental su entendimiento para con aquellos hombres y mujeres de los cuales nos había contado una versión que en algún sentido dignificara, a su vez que acusara todo lo que había ocurrido en un tiempo. Creo que es importante, es un hombre de su tiempo, si bien pienso que la gran contribución de Miguel León Portilla sobrevive al tiempo, también pienso que ha acuñado de cuya agua han abrevado múltiples artistas, múltiples escritores, ahora en lenguas originarias, que sin duda están haciendo una revolución con respecto de quiénes son, con respecto de la identidad, con respecto de México, quiénes somos los mexicanos, por qué somos como somos y por qué nos vemos como nos vemos. Y pienso que todas esas reflexiones no podrían haberse dado si no hubiese un inicio, y pienso que en ese sentido, en la historia, para entender la historia que tenemos ahora, para comprender a los pueblos indígenas en la narrativa nacional, me parece fundamental el agua, digamos, el abrevadero que se llama Miguel León Portilla.
This morning session, let me present Matilde Lalín. She did her PhD in University of Texas, and later on she visited many prestigious institutions, including Max Planck Institute in Bonn, EHES in France, MSRI in Berkeley, and the Institute of Advanced Study in Princeton. And now she's currently professor at the University of Montreal in Canada. So she will speak on L-function and Mahler measure.
Thank you very much. Thank you very much for the introduction. And primero que nada quería agradecer a los organizadores por la invitación. Estoy muy contenta de estar aquí. Yo estuve en México hace 26 años con la Olimpiada Iberoamericana de Matemáticas, así que es muy lindo estar de vuelta. I just said that I've been to Mexico for the first time 26 years ago for the Iberoamerican Mathematical Olympiad, so it's really nice to be back. So I'm going to be talking about L-functions and Mahler measure, and really to number theory and beyond, kind of Toy Story sentence. My goal here is to tell you about this part of my research that I do, but one thing I want to make sure is that you care about the elements in my theorems. So for that, I'm going to be doing kind of like these videos when you start from outside the planet Earth, and then you zoom, and you approach a person, and then you keep zooming, and you approach maybe a cell. So I want to do a little bit like that. So I'm going to start very, very general, okay, talking about what number theory is about, or at least according to me. Okay? So I think of number theory as a study of integer numbers or natural numbers, okay, and the things that can be constructed from them. And so when you study objects, you can see them, in a sense, from 2 points of view. So one is what they are made of, okay. So natural numbers are made of prime numbers, okay. And also, you can see what can you do with them. So it's kind of the outside. So the outside is maybe, for example, solving equations, solving problems, okay. So here by equations, I'm thinking of Diophantine equations, right? So polynomial equations, and I'm interested in, in the way I'm writing things, I'm interested in natural solutions, but I mean, it could be rational as well, obviously. Now, okay, so if we look at the first point of view, the point of view of prime numbers, okay, every natural number is a product of numbers, of prime numbers in a unique way, okay, and we know there are infinitely many primes, okay. We could ask more precise questions, such as, what's the distribution of the primes? So if we look at the function pi of x, that counts the number of primes up to x, any real number, we could be studying this function. And what is known, and this goes back to Gauss, is that this function, pi of x, can be approximated by, for example, this li of x, or li of x, is the integral between 0 and x of dt over log t, or, okay, so that's maybe complicated, but also this can be approximated by x over log x. So typically we think of, the number of primes up to x as x over log x. Okay, so this doodle here is really like an asymptotic approximation, so it's an error term. To be concrete, okay, so here's a table showing a little bit of how well these functions approximate in some examples. So the first column is some powers of 10. The second column is the number of primes up to this power. Then here you can see how x over log x approximates. Okay, so it's a difference. And you can see, okay, so this is the error term, okay? But you can see it's smaller than this number, okay? And then here's how li of x approximates. So you can see that li of x is much better approximation. So people are interested in this. understanding the distribution of prime numbers. And so for that, I want to talk a little bit about the Riemann zeta function. So the Riemann zeta function, we can think of it as defined as the sum over n from 1 to infinity of 1 over n to the s. And well, initially, s was an integer greater than 1, okay, unit greater than 1 for this to be convergent. But then you can, in principle, you can extend this to complex numbers with real part bigger than 1. And then it was Euler's observation that actually you can write this as an infinite product over the primes just by using prime factorization. Okay, so the Riemann zeta function has some nice properties, and these properties will show up again in another L function, so they are kind of key. So one is the Euler product that I just showed you. Another is the functional equation, okay, and this is attached to a meromorphic extension to the complex numbers. So I'm going to talk a little bit more in the next slide. There is a Riemann hypothesis. Well, this is a conjecture, but well, we expect it to be true. And also there are special values. And here I mean in a very general way, some values of zeta are interesting for different reasons. So here are some examples. I mean, it's very general. So for example, well, there is a pole at 1, okay, so the harmonic series doesn't converge. And that pole, well, we'll talk about, but this is connected to having infinitely many primes. So it's information, it's arithmetic information about that number. Zeta 2 is pi squared over 6, okay? And so that was a problem that was an open problem for many years. Zeta 3 is a conjecture that is transcendent, but it's not known. We know that it's irrational. Okay, so there are many questions around those lines. Okay, so in terms of the functional equation, I just wanted to show you what it is. Okay, so if you modify the Riemann zeta function by some factors involving especially the gamma function, okay, there is this functional equation. So basically, if you take the left-hand side as a function, then on the right-hand side you have the same function evaluated in 1 minus s. So you relate s and 1 minus s. Okay? So graphically, what you can say is that what you know, say when the real part of S is greater than 1, okay, the initial definition actually translates into some information about the real part of S less than 0. Okay. And so this part is something that can be understood very well, and so this part can be understood very well. So let me talk a little bit about special values. Like I said, okay, I said that zeta 1 is a pole, okay? So if you take the Riemann zeta function and you take the log, okay, this is more or less like the sum over the primes of 1 over p to the s. And then the fact that the harmonic series diverges translates into log of zeta 1 being infinity, and then the sum of 1 over p being infinity. So there are infinitely many primes, okay? I like these lines because they are all kind of wrong, the way they're written, but I mean, you get the idea. And so there are infinitely many primes, but this is more, I mean, okay, so there are, you know, it says, it's not just, you know, to conclude infinity will be maybe the sum of 1, but you are saying more than the sum of 1, you're saying the sum of 1 over p. So in general, the idea that I want to transmit is a location of things about the special values about the Riemann zeta function gives information about the distribution of primes. Well, the main thing about the Riemann hypothesis is about the location of zeros. So let me talk about the zeros, okay, from the functional equation, from the poles of the gamma function, you can actually see that there are zeros in -2, -4, -6, etc. All the negative even numbers, even integer numbers. But like I said before, this question mark, what happens when the real part of S between 0 and 1? Okay. And the conjecture, okay, so the Riemann hypothesis, what claims is that the zeros in that what is called the critical strip, they have to be actually at the axis of symmetry. So they had to be with real part of S equal 1/2. And what is this good for? Okay. Well, without knowing the Riemann hypothesis, actually one can give a more precise statement about how Li approximate pi of x, and with certain error term, and with the Riemann hypothesis, you get a much smaller error term. Okay. So that's more or less the basic of why we care in principle about the Riemann zeta function. Okay? Any questions? Okay, so what you need to get now is just we care about the Riemann zeta function. Next. Okay, next is the second part of what we look at integer numbers. So the second part I said was, what can you do with them? Okay, and I said equations. Okay, so generally for me an equation will be a polynomial in several variables with integral coefficients. And what we are interested, like I said, is to find integer or rational solutions. So, well, this one is pretty easy. But, you know, we can change, okay? X squared plus y squared equals z squared. Okay, so that's the Pythagoras theorem. Okay, so then you have many solutions, okay? So the Pythagorean triples. And so the question in general, there are several questions that one could ask. Okay, so if you give me an equation like that, well, does it have solutions? How many solutions does it have? And obviously, which ones? Okay, so find the idea would be to just be able to list the solutions. And those questions can be answered to some extent to degree 1, 2, and greater or equal than 4. And because this is an algebra colloquium, I can be more precise than that. Okay, so what I mean is really when you have genus 0 or genus greater than 1, we know something about this. Okay, it doesn't mean that we have the final answer, but we can say a lot in general. The big question that remains is genus 1 or degree 3. Okay, those two things are not necessarily equivalent. Oh. What happened? It's, sí. ¿Sí? ¿Y sigo ahí? Okay. Okay, I'm going to continue here for the time being until that screen starts working again. Okay, so what I was saying is that, oh, great, a case that is more complicated in a sense is a case of genus 1 or degree 3 that corresponds to elliptic curves, and roughly speaking, we could think of an elliptic curve as an equation of the form y squared equals a cubic polynomial. And if you try to understand, say, the solutions of these, well, one thing you could do is to try to graph this in the reals. Okay, so depending on whether your cubic polynomial has 1 or 3 real roots, you will get this graph or this graph. Okay. Now, okay, so what can we say about this type of equation? Okay, well, here is an example. If we take y squared equals x cubed plus 17, then there are many solutions. Okay, you have, and there are, you know, lots of variation. I mean, nice simple solutions, ugly solutions, etc. And there are infinitely many, in fact, that you can prove. If you change the 17 by -3, suddenly there are no solutions in the rationals. Okay. So the understanding of the number of solutions is something that is complicated. Before I go on, let me mention, because I'm not going to use this in my talk at all, but you cannot say elliptic curve without mentioning that there is a group associated to it. Okay, so the points on an elliptic curve form a group. And let me just mention what I mean by that, okay? So if you have 2 points, P and Q in the curve, you can take a line joining these 2 points, and it will intersect the curve in a third point. Okay, this could be, you kind of need algebraically close, but okay, so for the, yeah, I don't want to draw a picture in the complex numbers, okay? So you take the third point of intersection, and then if you take the vertical line in this picture, the second point of intersection will be what is called the P plus Q. So if we want to, you can define this operation, P plus Q, and it will give this point. And this operation gives an abelian group. And in fact, over the rationals, this is going to be a finitely generated abelian group. So it's super interesting. But then, of course, I mean, if you don't know if there are finitely or infinitely many solutions, well, I mean, I mean, we can say question about is your group finite or infinite. Okay, so one thing that we do to study elliptic curves is we associate to them a function, a complex function, that roughly speaking counts the number of solutions modulo P for every prime P. And this is like a complicated sister of the Riemann zeta function. And I'm just writing it as an Euler product. So remember that the Riemann zeta function has this Euler product, 1 minus 1 over P to the S to the minus 1. Okay, so this is made of something very similar, except that here is something like degree 2, in a sense. So it's not just P to the minus S, it's P to the minus 2S. And there is a coefficient here that counts, roughly speaking, the number of solutions modulo P. Okay, so it's actually P plus 1 minus the number of solutions. And one more thing, okay, so this is technical, but I have to mention it. So there is the good primes and the bad primes. Okay, so the bad primes are the primes such that when you reduce your elliptic curve modulo P, it doesn't stay an elliptic curve. Okay, so it goes to genus 0. And so those are finitely many, okay? And most of the terms are going to be like that. Okay, and so for this L function, we can go back to what the list of properties that we gave for the Riemann zeta function and make a similar list. So there's an Euler product. Well, I use it to define it, in fact. There's a function equation. In this form, it relates S to 2 minus S. Okay, there's an exclamation point because this is far from obvious, so it was a big theorem. Well, you could ask about the Riemann hypothesis. You can imagine if we don't know about the Riemann zeta function, in this case it's more complicated. And you could also ask about special values. Okay. So my point here is that we care about this L function. Okay. And the thing I care about the most is the special values. Let me just say one more thing, okay? That what happens to this L function at 1, okay, is conjectured to give us information about the number of solutions. Well, whether they are infinitely many or not, and this is a Birch-Sinerton-Dyer conjecture. Okay. Okay, so both the Riemann hypothesis and BSD are among the 2 of the 7 millennium problems from the Clay Mathematics Institute. Okay, so I'm going to leave elliptic curves now for a little bit, okay? But the moral of the story now is that we care about elliptic curves, and we care about these L functions associated to them. Okay, questions? Okay, so now I'm going to go back a little bit to different type of problem. Okay, so again, talking about primes. Okay, so a question that is always kind of up in there is about generating large primes. Okay, and so I just want to mention Mersenne primes. Okay, it's the sequence 2 to the n minus 1, and well, each time I talk about Mersenne primes, I have to go online and check which one is the largest. So this is fun. So now we are up to 82 million something. Okay, so it has 24 million digits. Okay, so obviously, yes, we don't know if there are infinitely many Mersenne primes. Now, the construction of Mersenne primes is interesting because the fact that the numbers are of the form 2 to the n minus 1 restricts the kind of divisors, so it gives a congruence conditions on the kind of divisors that you could have. And so it's easier to check, if you give me a number, and this number happens to be of the form 2 to the n minus 1, it's easier to check whether it's prime or not than any sort of number of the same size that doesn't have this structure. And so this construction was generalized, in fact, like 100 years ago, 101 years ago, so it was proposed by Peirce. If you start with a monic polynomial with integer coefficients and roots Ri, okay, you consider the product of Ri to the n minus 1 over all the Ri's. And it's an easy exercise in Galois theory, maybe, to see that this product is an integer number. Okay, so this delta n is an integer. And obviously, if you start with x minus 2, you get the Mersenne sequence. Okay? But the point here is that, well, maybe with other polynomials, you could generate other large primes. So that was a question really 100 years ago. And a few years after, Lemmer was studying these sequences, okay? And what he realized was that improving the chances of having a prime, in a sense, depended on having a sequence that grows very slowly. Okay. The idea is that your chances improve if your n is big. Okay. So again, if you have a number that is given by some delta n, but you want the n to be big. So for that, you want the delta n sequence to grow slowly, so it goes backwards. Okay, and then he studied this quotient to kind of estimate this, okay? So it's natural to take the quotient of delta n plus 1 over delta n and see what happens in the limit. Okay, and it's not hard to see that if you take each of the factors, because this delta n is made of these factors, r to the n minus 1, okay, you're going to have absolute value of r if the absolute value of r is greater than 1, and 1 if the absolute value of r is less than 1. Now, if the absolute value of r is 1, okay, you may run into something cyclic. But, okay, so this is a motivation for the next definition. We're not going to worry about that. So my definition, okay, I want to kind of extract this limit. Given if you give me a polynomial, I want to have this limit. So it's going to be, I take, okay, so if my polynomial is not monic, I just take the leading coefficient. They are, okay, take the absolute value. And then I take the product of the absolute values of the roots that have absolute value greater than 1. Okay, so this is inspired by this limit that I mentioned. And this is going to be called Mahler measure, and I'll tell you why in a few slides. I mean, why it's called Mahler. Often, for me, I will be working with the logarithmic version. So that's just you take the log. So going back to what Lemmer was looking at, what you want is, you want a polynomial such that the Mahler measure, the capital M of P, is greater than 1, but close to 1. Okay, so you want greater than 1 because you want your sequence to grow, otherwise you are not going to find a large prime there, but you want the sequence to grow slowly. Okay, so in terms of the logarithmic version, okay, just take the log. Okay, so one question I want to get out of the way is when the small MP is 0 or when the big MP is 1, okay? So this was answered by Kronecker without this language, okay? But essentially, a theorem by Kronecker translates into saying that the Mahler measure of a polynomial with integer coefficients is 0 if and only if the polynomial is a product of a monomial and cyclotomic polynomials. In other words, the roots had to be roots of unity or 0. Okay. So that question is well understood. And the next question is, okay, so you want a small m of p positive, close to 0. Okay. So can you approach 0? And so Lemmer asked this, and he didn't even say this is a conjecture that you cannot approach 0. He said, is it possible in his paper? And the conjecture is no, and we don't know the answer. Also, it's a conjecture, precisely. Lemmer found this polynomial in his 1933 paper that had the smallest value for this Mahler measure thing. And he said, well, this is the best I found, okay? And actually, we don't know today whether this is the best polynomial or not, okay? So after invention of computers and everything, we still don't know. Let me just tie it up with the original question, okay? So with this polynomial, Lemmer found this prime number. So it's not that the delta is prime, but it's the square of a prime. Okay, so in terms of finding big prime numbers, we are kind of ahead of that, okay? But in terms of the question, Lemmer's question and everything, this remains open. Okay, now the object I'm interested in is the generalization of this Mahler measure to multiple variable polynomials. And the way you do it is by a complex integral, okay, where you integrate each of the variables of the polynomial. And what you integrate is log of the absolute value of p, okay? And each of the variables moves in the unit circle, and you do that with respect to the Haar measure. Okay, why? Okay, so if you go back to the one variable polynomial and you use Jensen's formula, you recover exactly the definition that I gave you before, okay? And this is the reason I always work with small m, okay? So it's the one that given naturally by the integral. Okay. So the first question will be, why will you do this definition? Okay, well, sure, it generalizes, but why do we care? Okay, so this definition was given by Mahler in the 1960s, and the reason he cared about it was because he was interested in heights of polynomials. So if you have, say, a polynomial, well, here I wrote a Laurent polynomial, but I mean, you can think just a polynomial. For example, you can consider the length, L of p, is the sum of the coefficients. Okay? And in a sense, it measures the complexity of your polynomial. And what happens, what Mahler proved was that this length is bounded by below and by above by this Mahler measure. So I should have said from the very beginning, the Mahler measure is not a measure. Okay? And here you can see it is actually a height. But the thing that is nice about this construction is that this Mahler measure is multiplicative. And so you can use the multiplicativity to say something about the length of the factors of a polynomial. So if your polynomial factors, and you want to compare the length of the factors with the length of the whole thing. And so that's what Mahler was interested in, and this has applications in transcendence theory. Now, what I'm interested in actually originated some years after. Oh, I forgot, I wanted to mention that. Okay. One thing is that when you have this multivariable Mahler measure, actually it turns out that it's a limit of one variable Mahler measures. So if you have a polynomial in n variables, you could replace all the variables, each of them, by powers of a single variable, perhaps forgetting about the one of them. Okay, that's why the first one doesn't have a power. And then you take the limit as all these exponents go to infinity independently of each other. So not what is written there, because writing this precisely would take the whole slide, okay? But basically, you don't want to take a limit where, say, K3 is always twice K2, okay? You want them to be independent. And so when you do that, you get the Mahler measure in variables. So from the point of view of Lemmer's question, this multivariable Mahler measure doesn't say a lot. Obviously, if you can find a multivariable polynomial with a small measure, well, I mean, you get infinitely many, you know, I mean, if something with, say, measure less than the Lemmer's polynomial, then you will get infinitely many one-variable polynomials with measure less, but finding such a polynomial is harder than looking at one-variable polynomial, so it doesn't really help with that. Now, what I'm interested in is actually exact formulas. So this came a few years after. So like I said, Mahler made his definition in the 60s, and then for a while, people just were looking at this as a height. And then Smith came in 1981 and actually sit down and compute the Mahler measure for some polynomials, some simple polynomials. And then what he found was special values of zeta function. For example, 1 plus x plus y plus z, so 3 variables, is given by 7/2 pi squared times zeta 3. Okay? So remember that I have a pi squared dividing in my integral in front, so you could, you know, that is not so burdensome to have this pi squared there. It's essentially zeta 3. Okay? So, what this does is that this describes zeta 3 as an integral that in fact, okay, it's an integral of a logarithm, but logarithms are integrals of actually rational functions. So this describes zeta 3 as an integral of a rational function that is the obvious ones that we know. So it's something that, it gives something about zeta 3. For example, there are proofs that zeta 3 is irrational by using integrals of rational functions. And not Aperi's original proof, but other proof that came later. So this is kind of tantalizing. Other equations that Smith found had to do with the special values of Dirichlet functions. So Dirichlet function is like the Riemann zeta function, but you twist, you put a character in the coefficients, okay? So in this case, it's a character of conductor 3, so it's a cubic character. It gives 1 if n congruent to 1 mod 3, minus 1 if n congruent to minus 1 mod 3, and 0 otherwise. So again, it's a very similar formula. And I just wanted to point out, because I didn't discuss Dirichlet functions, that they are, in a sense, very similar to Riemann zeta function. They satisfy also a functional equation, and is S goes to 1 minus S. So this equation can be written using the problem is there is a 0, and so when you do the functional equation, you end up with the derivative. Okay, so it can be written really nicely like this. And actually, this one also can be written with zeta of minus 2. Okay. Now, okay, so after Smith's result, people started looking at seeing if they could find other formulas like that, okay? So here's a family, actually, of n variable polynomials. Well, technically not polynomials, rational functions in the way I'm writing them, but this is, we could multiply by the denominator and get a polynomial that has the same measure, so that's it didn't fit the slide. So for example, here we have 1, 2, 3, 4, 5 variables, and we get 93 over pi to the 4th zeta 5. Okay. And there are known formulas if you replace your 2 by n. Okay, so there are known formulas. It's just they are not as nice. I mean, after 5, they have more than one term. But regardless, they are very interesting. So one thing that we want to do is we want to understand these formulas. Okay, so I mean, these formulas are very intriguing, right? I mean, I spent time talking about the Riemann zeta function, special values of the Riemann zeta function, and we care about them. Another example, if I look at the family x plus 1 over x plus y plus 1 over y plus alpha. And here alpha is a parameter, okay, and so it's a two-variable polynomial with a parameter, okay, so alpha can be 1, 2, square root of 3, whatever. And so for every alpha, you know, you can compute the Malloy measure of this two-variable polynomial, and so that gives you a function of alpha. And let me just say, okay, in preparation for the statement, okay, that this polynomial corresponds to an elliptic curve. By corresponds, I mean that there is a birational transformation that you can turn this polynomial in a Weierstrass form, okay, meaning in this context, y squared equals a cubic polynomial, like I said before. Now, in 1998, Boy published a paper with a lot of experimental computations that show a lot of examples like this, okay, where essentially m of alpha is numerically given by the L function of the elliptic curve that corresponds to the polynomial, okay? So L prime is 0, or if you want, is some L in 2, okay? So remember there is this symmetry divided by some rational number, S alpha, that will depend on the alpha, okay? Why do I divide by a rational number? Because often this rational number is an integer. So it's more intuitive to write it divided by S alpha. And S alpha is low, I say it's low height. So what I mean is that the numerator and denominator are small. So like 1, 2, 1/2. More precisely, here is a list of the first 20 values. Okay, 4 doesn't give you an elliptic curve. So 4 is not there because it doesn't give you an elliptic curve. But actually, the Malloy measure there is related to the L function of a Dirichlet L function. It's something that one can prove. Okay, and all the others, in principle, when Boy published them, they were conjectures. Now the red ones are proven. I didn't mention, I should have mentioned in my previous slides, what N is. Okay, N is the conductor of the elliptic curve. So the conductor, roughly speaking, the conductor of an elliptic curve is the product of all the primes of arc reduction. So it's the primes that, when I remind you, is the primes that when you look at the curve modulo P, you get you don't get an elliptic curve anymore. Okay, so this is roughly speaking. I mean, there are also, I mean, what I say is already wrong because you see 24. Okay, so 2 can show up with some exponent. So like I said, and here the S alpha, you can see in most cases this is an integer, but well, some of them are rational. Okay, and one thing I want to point out is that in this list, the curves that have been, the identities that have been proven have low conductor, and that's not by chance. Okay, so why do we get nice numbers? Okay, whatever nice is. Okay, why do we get special values of the Riemann zeta function or special values of L functions of elliptic curves? Well, this has to do actually. These identities can be interpreted in the context of some very general conjectures, the Beilinson conjectures. Okay, in the context I'm describing, you can think of them as a crazy generalization of the Wirisch-Sinerton-Dyer conjecture, where a special value of an L function is related to some number that is called a regulator. So I wrote a version here that is very vague. And let me just say the X is not just an elliptic curve, okay, it's a motive in general. So this is a very general context, and you can make an effort and understand these formulas in this context. And here also let me just point out that this is what this similar means that is equal up to a rational number. Okay? And so in many cases, just understanding the rational number is a question. Not just understanding this object. And basically what happens is that you can think of the integral that the Mahler measure is as calculating this regulator. Okay? So this connection was discovered by Denninger and also studied by Rodriguez Villegas, more or less at the same time as Boy's paper. This connection actually is already very helpful to understand the formulas with zeta n. In that case, it's not the Beilinson conjectures, is more like the Borel regulator. So it can be seen, we can see all these identities with zeta 3, like Smith's formula, zeta 5, as an evaluation of a Borel regulator. Let me say a few words about how the formulas involving the elliptic curves are proven. I'm not going to explain this, but there are a few methods or cases. So the first cases were proven when curves had complex multiplication. And in fact, those are with alpha, that is like alpha squared is an integer, but not alpha. So the reason, sorry, let me go back. So the reason complex multiplication is important in this case is because the L function has a special shape that can be related to the integral. Other cases were again proven by relating the L function to some particular products of Einstein series that then can be related to the integral. And then more recently, Bruno, Méli, and Sudilin discovered a method that is a little bit more systematic. So you parameterize, if you can parameterize your equation by modular units. So modular units are some sort of modular forms that have zeros of polar curves. So if you can parameterize this, then, well, essentially you can prove this relationship with the L function. And in fact, all the cases that I gave you in my previous talk, even though in my previous slide, even though some of them were originally proven by this method, they can all be seen by this modular unit parameterization. Now, the issue is that actually there are only finitely many conductors, finitely many curves that can be parameterized like this. So this won't prove the whole list of Boy's results. One thing I want to say is that once you know you have a formula for a certain curve with certain conductor, there is a good chance that you can use the regulator, Beilinson regulator, to actually prove other formulas that have, well, I wrote the same conductor. It's really when there is an isogeny. Okay. But okay, all of this is an art. So the conclusion, this slide is a little bit maybe specific and detailed, but what you need to get out of this slide is the fact that this is an art, and each identity can be a paper, say, okay? So each identity requires new ideas. Let me mention other cases that have, are being considered, etc. So there's a recent preprint of Liu and Kim where they actually went a little bit farther than Boy and look at families of curves of higher genus. So Boy, his paper is mostly genus 1, but some cases of genus 2. But for example, here's a family of genus 3. And the conjecture is given by, again, the L function of an elliptic curve. So basically what happens is that the Jacobian of this splits as a product, and one of the factors is an elliptic curve. For example, for that, we've been able, with Gang Wu, one of my PhD students, we've been able to actually relate the Mahler measure to the Mahler measure of a genus 1 curve. And, well, this obviously is conjectured to be given by that, okay? But what we know is this is related to that, okay? So kind of along the lines of what I was saying before. Other intriguing identities, and there are many of them, but I mean, all the cases I show you with elliptic curves is L prime of E 0 and two variables. So here is an example, it's numerical. Okay, this time I have a question mark, it's just a computer says this coincides to 20 decimal places or more. And we have a 3-variable polynomial, and now the L function of the elliptic curve is -1. So this is like L in 3. Okay. And so this was discovered by Boy, and we studied this relation, and we actually proved that this Mahler measure was also related to some other object. Okay, so this is still a question mark. Okay, so we don't know, but this can be studied with the Beilinson regulator as well. I wanted to mention other. So I said number theory and beyond. So here's the beyond. If you start looking at, so I gave you one example of Smith was 1 plus x plus y. If instead I put coefficients there, so a plus bx plus cy, okay, so a, b, and c are parameters, and I still have a two-variable polynomial, then actually one can prove a formula that is actually very concrete and nice. I mean, obviously it depends on a, b, and c. There are two cases. So your a, b, and c, if you take the absolute values, okay, so it's easy to see that this Mahler measure only depends on the absolute values of a, b, and c, so you could think of them as positive numbers. If you take positive real, if you take those numbers, they could be the size of a triangle or not. Okay. So if they are the size of a triangle, you get a formula. So alpha, so if you take the triangle here, and alpha is the angle opposite to A, and beta to B, and gamma to C, then you will get these terms, okay? So each angle multiplying the log of the opposite side, and then some term with the D, depending on A, B, gamma, essentially depending on the triangle. And that term actually is given by a dilogarithm, and it corresponds to a volume in hyperbolic space. And it's actually, I don't want to go into detail, but this is actually the ideal hyperbolic tetrahedron that you can build in the upper half space model of the hyperbolic space that has basis exactly this triangle, and the 4 vertex as infinity. And then if A and B, C are not a triangle, then it's a very simple formula. So actually, Smith's case is a equilateral triangle, and all these terms goes away, and then is a dilogarithm, and this dilogarithm is a the function that I showed you earlier. Let me mention very quickly that there are other more, say, deeper, maybe, relationship with topology. So in terms of hyperbolic volumes, Boy found, for example, that the A polynomial, so if we have a knot, you can build a knot, a hyperbolic knot. You can build an invariant that is called the A polynomial, which is not the Alexander polynomial. It's a two-variable polynomial. And if you compute the Mahler measure, often this ends up being related to the volume of the hyperbolic knot. Well, I should say hyperbolic knot complement. Okay. So in this case, it's a particular knot, this knot. Okay, so it's called the figure 8 knot because it looks like a figure 8. And the volume is given by the Mahler measure of this invariant. In topology, in general, you have tons of invariants that are polynomials, and so people like to compute Mahler measures of those and see relationships. One thing that is striking is that the Lemmer polynomial, the degree 10 polynomial I showed you earlier, shows up as an Alexander polynomial of a link, so the -2, 3, 7 pretzel knot, and it was published in a paper in 1933 at the same time as Lemmer's paper, completely independent. So there were, in 1933, 2 papers came out with this degree 10 polynomial for different reasons. So here's another depiction of the pretzel knot. Okay. Okay, so I want to very quickly mention that what we are working on lately has to do with changing the integration torus. So I said I was integrating my variables in absolute value 1. So we've been experimenting with, well, changing the radius of each variable. And this, actually, you can, for people in tropical geometry, you can relate it to actually the ranking function. I don't know much about that, but okay. Studying this object is interesting not just in number theory. And we've been able to prove some formulas. So like putting a parameter and seeing this deformation of this Mahler measure. So the formulas are similar. Sometimes, okay, they still involve the L function, but they have some terms coming from this deformation, exactly like the formula of A plus Bx plus Cy that I showed you before. So these are students of mine, by the way. And there are other things that people have been looking at, putting different coefficients. So this is not exactly enlarging the torus, but it's just other coefficients. So the original family by Boy, and then I put some coefficients. So there are nice formulas like that. And then even back to some of Boy's conjecture, there are some conjectures involving like the elliptic curve, like the Weierstrass form of the elliptic curve directly given by that. And so we've been looking at these things. So one of my students, for example, proved a formula for certain values of these two parameters. Okay, so we've been looking at this lately, and why these formulas, from the point of view of Bayes-Linson conjectures, they actually stretch a little bit the application. So I didn't give any details about that, but essentially, this regulator, the way it connects is like it's a regulator evaluating some K-theory. But what happens is that when you put these coefficients, you kind of leave your K-theory. So you have something that is called non-trivial time symbols. And so it makes the interpretation much more complicated. It's like a relative K-theory. So these formulas are very interesting from that point of view, understanding why this works, when this still works also. Okay? So when can you do this deformation and push your formulas further? So in sum, this is a summary of what the things that we would like to understand in terms of Mahler measure. So definitely Boy's formula in a systematic way. Okay, by systematic I mean, for example, understand what this coefficient is, how it works. So obviously, being able to prove them. Mahler measure of higher genus curves. Okay, like the one I showed you, genus 3. Well, the cases we've been looking always have like some these elliptic curve factors, but I mean certainly there are many other questions more general. Formulas involving L prime of E at beyond, not just at 0, but beyond. Okay, the formula I show you with -1. Okay, it could be minus other things. The role of changing the integration torus, like I said before. Okay, and another case with non-trivial coefficients. Okay, and so in the end, what we hope is that these formulas can shed some light to further understanding of Bayes-Linson conjectures, okay, and understanding what the nature of the values of these L functions. Okay, and with that, I thank you very much for your attention.
Talk. Do you have any questions? Yes, please.
Yes. You have Mahler measures also if the variable is p-adic. Have you considered that case, zeta functions?
They are not me, but yes, some people have studied p-adic versions. Yeah, they are complicated, but yes, certainly. So there's some work of Besser and Denninger on that.
Okay.
And, yeah.
Thank you.
I actually have a very minor historical question. So you said that nobody has found a polynomial better than Lemmer's, even now with computers. But Lemmer was a computer pioneer. I mean, in the 30s, he wasn't using electronic computers, but he was using all sorts of machines with wheels and bicycle chains. Did he use such computers to find that polynomial, or did he do it all by hand?
Actually, I don't know. To be honest, I don't know the story. But yeah, I didn't mean to say, that Lemmer wasn't doing computation. I mean, he certainly has a very, I don't know if he did by hand or not. Because he certainly has a very systematic, he has quite a few polynomials in his paper. So it's a great job.
Are there more questions?
Thanks. In the first of your presentation, you see two different ways to follow this presentation. But are there another way to focus on this kind of the investigation or your work? At the end, you explain us the topology or the relation with this, but in the fundamental question, are there another, perhaps you think in another case, you can see another option to follow or to create in another system, numbers, or give the reinterpretation of this?
I'm not sure I understand. So do you mean to reinterpret this in terms of to do a different construction, or okay, let me give you some
perhaps
directions. So people have generalized this. Okay, so one way you could think, you can actually see that these integrals at the end of the day, you are evaluating like a residue, and so you can think of it. You can think of the Mahler measure as the integral of some function that is actually a series where each coefficient, for example, counts a constant coefficient on a polynomial. And from that, this idea can be extended, and then you can define the Mahler measure over finite groups, for example, or over groups in general. I don't know. So people, for example, people have been studying that. So that's a very active area of study that I didn't mention. For example, Lemmer's question over finite groups. So that's definitely a direction. Also, Mahler measure appears as the entropy of some systems, some dynamical systems. So there is also some direction there. I don't know if.
Thank you.
Any more questions?
Hi. So since we're in Mexico, I'll ask my question in Spanish. I hope it's okay. Mi pregunta es similar un poco a la de Luis, en el sentido de lo podríamos hacer sobre los pedádicos y tú nos cuentas que sí, que hay gente que lo estudia, pero existe una versión adélica en la que, como a la Tate, en que se estudia todo el tiempo, tú sabes si alguien lo hace o si no lo hacen o por qué sería difícil, combinando como la idea de también puedo cambiar los toros por grupos algebraicos más general. No sé, es medio meta pregunta basado en lo que pregunta Luis. ¿Tú sabes si alguien ha hecho una versión adélica de esto? ¿O si existe de hecho una versión adélica?
No, Vincent Maillot has explored this a little bit, but I'm not completely to the top of that.
Okay, gracias.
Yeah.
And maybe I have a question myself. When you show this Mahler polynomial, which has a relatively high degree, what struck me is that there are very few change of sign in the coefficient. It's plus, minus, plus. And I think this plays an important role in the Sturm algorithm to see where the real polynomials are. Is it involved in this Lemmer construction?
Okay, so in terms of changes of signs,
yeah.
that no, I'm not aware of that. But okay, one thing that I didn't discuss much of this polynomial. I should have. Is a reciprocal polynomial, so it's palindromic. The fact that the coefficients are plus, minus 1, or 0 is also related, in a sense, to Mahler measure. You want small coefficients to have, small height in the coefficients or small coefficients to have good chances of have a small measure. And finally, there are some more recent works, maybe from the 2000s, of Mossinghoff, maybe Baller, where they look systematically at products of cyclotomic polynomials with some small modification. And the Lemmer's polynomial comes from that. So it's essentially a product. Okay, so what do I mean by small modification, I should say? So it's like, you add a monomial or something, or you add a degree, like just x plus 1 or something like that. And Lemmer's polynomial comes from there. And a heuristic is that basically cyclotomic polynomials are the ones that have measure 0. And so if you modify them a little bit, your measure shouldn't change much. So it's this mentality. But I don't know anything about the number of changes in the sign.
Okay, and also, is it clear or not correct that these Mahler measure are periods in the sense of Zaghi?
Oh, definitely they are periods. Yes, I should have. I kind of tried to mention, but I was worried to get to the end. So yes, definitely. So you take your log. You can replace log by the integral of. Okay, and so your integral defining the Mahler measure, you can replace it by the integral of a rational function. So definitely they are periods, and definitely from that point of view, these identities are super interesting as well, because one of the big questions about periods is whether when you have some relationship between periods, can you prove it using okay, so a set of basic operations, Stokes theorem, such as that, between integrals. And so that's also kind of behind the spirit of that, yes, of what we are doing.
Okay, so thank you very much for this very nice talk, despite some technological problems, and we'll thank the speaker again. Okay, now we'll continue with the last talk of this morning with Daniel Labardini. He's from UNAM, but before being here, he did his PhD in Boston with Andrei Zelevinsky, and is an expert of combinatorics, convex geometry, and hyperbolic geometry. So thank you very much.
Thank you, and thanks to the organizers for the invitation. It's truly an honor to be here. And then I'm going to tell you a little bit about cluster algebras, hyperbolic geometry, and generic bases. So cluster algebras were discovered or invented by Fomin and Zelevinsky almost 20 years ago. And there are two aspects that have pervaded cluster algebras in those almost 2 decades, which are, on the one hand, the connections with other areas of mathematics and even some connections with theoretical physics. And the other aspect is that a lot of people have been looking for bases for cluster algebras and understanding them. And somehow the purpose of this talk is to illustrate these two aspects, to give a little bit of the flavor of these two aspects. I have tried to leave as many, to swipe as many technicalities as possible under the rug, but I think it will be inevitable at some point to become a bit technical. But okay, so what is a cluster algebra? A cluster algebra is some sort of ring whose generators one produces recursively, applying a combinatorial operation called mutation. And this operation is really defined in 2 levels. One is it's in the purely combinatorial level on directed graphs, and then there is an algebraic lift. So once one has the notion of mutation on the combinatorial level, one lifts it to the algebraic level to mutate tuples of rational functions. So let me start with the purely combinatorial side, which is the side of mutations of quivers. So a quiver is a finite-oriented graph, and then let me assume that it's 2 acyclic. So it doesn't have oriented cycles of length 2, and well, also not oriented cycles of length 1. And then if we are giving such an object, a 2 acyclic quiver, and then we pick a vertex of the quiver, then the mutation of the quiver with respect to that vertex is defined by applying 3 steps, 3 combinatorial steps. Namely, in the first step, I look at the vertex with respect to which I want to mutate, and then for each pair of arrows, which are consisting of an incoming arrow and an outgoing arrow from the vertex, add a new sort of composite arrow from J to I. So this is for each pair of incoming and outgoing from K. In the second step, we reverse the arrows incident to the vertex we are mutating at. So if there is an incoming arrow, it gets replaced by, if there's an outgoing arrow, it gets replaced by an incoming arrow, and vice versa. If there's an incoming arrow, it gets replaced by an outgoing arrow. And finally, look for 2 cycles and delete them one by one. And the point here is that you see here, it could have been that originally there were some arrow from I to J, in which case in the first step I would be creating a 2 cycle. And I want the operation to stay within the class of 2 acyclic quivers. So in the end, I delete 2 cycles one by one. So example, here we 2 examples. So let's say here in the first one that I'm mutating with respect to this vertex 2. So in the first step, you see here I have an incoming arrow and an outgoing arrow, so I add this new arrow. In the second step, I reverse these other 2, so it becomes this. And then in the third step, I see that there is these 2 cycles, so I delete it, and then this is the result. And similarly in this other example, which is slightly more complicated, here if I mutate that 1, so you see, for instance, in the first step, I notice that, there is this incoming, outgoing, incoming, outgoing, incoming, outgoing, incoming, outgoing. So that's why there are these 4 composite arrows. Second step, reverse, the ones incident to the mutating vertex. And finally, delete these 2 cycles. So the result is this one, which, by the way, looks kind of similar to the original one, right? I mean, okay, so it's a fairly simple combinatorial operation, very, very, very easy to apply. Okay, and then sources of examples, right? So one natural source of examples comes from the triangulations of oriented surfaces with marked points. So for instance, here I have a disk with some points on the with some marked points on the boundary, and well, 2 triangulations, right? I mean, okay, and so how does this give rise to a quiver? Well, I can say, okay, I want the vertices of the quiver to be the arcs of the triangulation, okay, and then I'm going to use the orientation of the surface, because the orientation of the surface, of course, allows me, within each triangle, allows me to say what it means clockwise. Right? Okay, so I draw arrows clockwise. So this would be, if I start with this triangulation, this would be the associated quiver, and similarly here. Okay, now notice that these two triangulations are kind of almost the same, right? They differ by a very simple operation, which is the flip of this arc, right? So it's kind of, I look at this arc, and then it sits within this quadrilateral, and there is exactly one other diagonal that can replace it and form another triangulation. So these 2 triangulations are related by a flip, right? And well, the thing is, the underlying quivers are then related by a mutation, and it's not a coincidence, and it's an observation made by several people in different levels of generality. It's not so hard to prove, but it's really it turns out to be like really essential in the development of cluster algebras associated to surfaces. So you see, like even like this part even looks already familiar, right? I mean, because it looks like this guy, right? I mean, so somehow at least for this triangulation, somehow I already checked that they are related by mutation. But okay, and now let me lift the operation of mutation now from the purely combinatorial level to the algebraic combinatorial level. So let's say that, let's take R to be one of our favorite rings, Z, Q, R, or the complex numbers, like whichever you prefer, and then let me denote by R parentheses x1 to xn the field of rational functions in n algebraically in n variables with coefficients in R. Okay, and then let's call a seed to be a pair consisting of a 2 acyclic quiver and a tuple of algebraically independent rational functions. Okay, and then we lift the notion of mutations of quivers to the level of seeds, right? So if I'm given a seed, so now it consists of a quiver and an n tuple of algebraically independent functions. And if you tell me, if you fix a vertex, then the mutation with respect to that vertex is another seed, defined by, well, at the level of quivers, we already know what we should do, right? So the underlying quiver is just the mutation of the original one, and at the level of rational functions, it's almost the original one, except in the kth place, where instead of lambda k, instead of the original kth member, we write this new rational function, which is constructed also in a very simple manner, namely, I mean, in the denominator, I'm going to put the old rational function, right? And in the numerator, what I'm going to do is I'm going to form two monomials, And these two monomials, I formed them by looking at the incidences, by looking at the arrows that go from K to another vertex, and then put the corresponding variable. And then on the other hand, look at the incoming arrows to K, and then put the corresponding variable. Right? So again, I mean, this is a new rational function that is also very easy to form. Right? Okay, and otherwise the other rational functions remain the same. So examples. So for the quivers that we had in a few slides ago, let's say that now I have my seed is this quiver with these three rational functions. Then the new quiver, well, I know that the mutation is this one, and then here I have to put. You see, it has to be lambda 1 plus lambda 1 is one monomial, and then plus lambda 3, which is the other monomial, then divided by the old one, which is lambda 2. And similarly, in this other example, we already know that this quiver is the mutation of this one with respect. Oops, sorry. Here it should be a 1, not a 2. Sorry. And the new seed would be, well, I look at the outgoing arrows, so it's 2 and 4, so it's lambda 2, lambda 4, and then the incoming arrows are 3 and 5, so lambda 3, lambda 5, divided by lambda 1. Okay. All right, and then the idea is, well, now we have a notion of mutation of seeds, which is if you give me a 2 acyclic quiver and a corresponding tuple of rational functions, then the mutation with respect to one vertex produces a new 2 acyclic quiver and a new tuple of rational functions. Okay, so the idea is now, okay, iterate in all possible directions, right? And then after all possible iterations, you end up with certain set S of rational functions, all the rational functions that appeared in the process, right? Which I don't know, S could a priori could be infinite, and then you take all those rational functions and declare them to be a set of generators for certain ring, which is the R sub algebra generated by them. Remember that R was this ring Z, Q, R, or Z. And that is the cluster algebra associated to your initial data. I mean, everything was produced from this initial data, from 2 acyclic quiver and a tuple of rational functions. Okay? And then the elements of X, then they receive the number of cluster variables. Okay? So example, I mean, I'm not going to give a full example of all the process, but maybe of a couple of iterations. So in this sort of old example, I start with this Q and this lambda. Then when I mutate with respect to 2, lambda 2 gets replaced by this one, and then now I mutate with respect to 1. Let's say so this lambda 1 gets replaced by this one, which then simplifies to this quotient. Right, and then let's say that I mutate against with respect to 2, then this guy gets replaced by something which starts looking not so nice, right? And then you see, and then I say, okay, then let me try to simplify, and then when in the process of simplification, then I suddenly realize that there is certain cancellation that makes the final result look nice, and by nice I mean, you see that the denominator is just a monomial, right? So you see here, for instance, here in the first one, the denominator is a monomial. Here as well, right? That is, I mean, even though at some point I divided by certain rational function, there was a way of simplifying to obtain a Laurent polynomial, right? And well, this always happens. And this is the Laurent phenomenon of Fomin and Celebinsky, which says if you give me any 2 seeds in the cluster algebra, so let's say you start with your seed Q lambda, and then you start mutating, and then you take any 2 seeds, right? And then the Laurent phenomenon, what it says is that the rational functions here can always be expressed as Laurent polynomials in the cluster variables appearing here. Okay, and then at this point, let me maybe mention some result. I mean, kind of in case I run out of time, at least I can mention a result where I was involved before running out of time. What Cerulli, Keller, Plamondon, and I proved was that the cluster monomials form a linearly independent set. So what is a cluster monomial? What we have now is we started with a seed, we started mutating, and then we obtained a bunch of seeds, right? And then if I take one seed, I can form the honest monomials in these rational functions, right? I mean, the monomials where all the exponents are non-negative in these rational functions in this seed, right? And then if I can take another seed and then form all the honest monomials with non-negative exponents in these other in these other rational functions, and so on. And I can do this at each seed, right? So somehow I can start forming monomials in seeds, but kind of somehow some sort of not mixing, right? Somehow like not mixing arbitrarily, like products of something in this seed and something in this other seed, right? So kind of do it in a kind of organized way, and any monomial that any expression that I can obtain in this way, I call it a cluster monomial, right? So hence the name cluster monomial, right? I mean, it's a monomial in a cluster. And the thing is, Fomin and Selevinsky had conjectured that they always were a linearly independent set. So we proved this, and somehow this brings me to one of the aspects I mentioned at the beginning, which is the search for bases of cluster algebras, right? So because somehow kind of the ideal situation would be that cluster monomials would always form a basis for the cluster algebra somehow. That's not true. That actually rarely happens. And then there has been many authors that have worked in different levels of generality and with very different techniques to try to produce bases for cluster algebras. So just to mention some people who have worked on bases, maybe I can say Musiker, Schiffler, Williams for surfaces with marked points, and then Lee, Ruppel, Televinsky on something they called greedy bases, and then some other people like Gross, Muller, Williams, Stella, Chung, in comparing these greedy bases with some like canonical basis that Gross, Hakinkill, and Kontsevich produced. So what they did was using some technology they called scattering diagrams. They produced certain things they called theta functions, which they showed to contain the cluster monomials and that form a basis of the cluster algebra. For a very large class of quivers, there is a slight technicality involved, so my point is there has been many people involved in the search of bases, and maybe I should also mention Plamondon, Fanzine, and other people. That I'm sure I'm missing someone. I apologize. But so I will leave this stuff related to bases in standby, because now I'm going to try to go to the relation with hyperbolic geometry, and then later I will try to come back to talk a little bit about bases of cluster algebras. This disk is really the Poincaré model of the hyperbolic plane. Of course, if you give me a full geodesic, it of course has infinite length, right? So if given a geodesic, I want to produce something which has finite length, well, maybe something you can do is kind of, okay, take horocycles based at the endpoints and use the horocycles to cut your geodesic, and then that way you have a finite segment, you can measure and get the real number, right? So that's an idea that Penner uses to define the lambda length between two horocycles, right? So if you have two horocycles, they are of course based at some points in the circle at infinity, and then you can use the horocycles themselves to cut the geodesic that connects the two points at which the horocycles are based. You can measure this length, right? And then you can take the exponential and then the square root, and Penner calls this number the lambda length, where there is some signing, right? So the thing is, you put a plus sign if the two horocycles don't cross, and a minus sign if the horocycles cross. So somehow you see it's kind of, if the horocycles, let's say, are tangent to each other, this d is zero. It's kind of the distance between them somehow is zero, right? So that, yeah, and then if they cross, well, negative, and then if they don't cross, it's positive, right? Okay, and then you later just modify with exponential and square root for whatever reason, right? Just because we can, and call it the lambda length. Okay, and there's this beautiful theorem which says, well, if you have any four horocycles in the hyperbolic plane, these lambda lengths satisfy the Ptolemy identity. That is, you see that the product of lengths of diagonals is equal to the sum of products of opposite sides. And the point is that this is true for every choice of four horocycles. And kind of the fact that this is true for any choice of four horocycles kind of starts suggesting that this is some identity that holds in some Teichmüller space. Okay, so now what I'm going to try to do is to interpret this Ptolemy identity as a change of coordinates in some Teichmüller space. So what would be a Teichmüller space, let's say, of a polygon, right? So fix a polygon, an oriented Euclidean convex polygon, like a combinatorial polygon, where you have numbered the vertices from 1 to n clockwisely. Okay, so and I'm going to think of this polygon as kind of as a combinatorially given polygon. And somehow the question I asked myself is, okay, so what are all the possible ways of putting a hyperbolic metric on this combinatorial polygon in such a way that the vertices become points at infinity, ideal vertices, right? But I'm going to do that, but also always remembering that there is a first vertex, so kind of that there is a marking. So if that's what I want, then I say, okay, then an ideal quadrilateral, it really is just determined by the 4 points at infinity, right? So all the possible ways to put a hyperbolic metric on my combinatorial polygon, well, it should be captured by just considering all possible 4 tuples of ideal vertices. Okay, so that's how I just defined the Teichmüller space of the polygon. So it's going to be the set of clockwisely ordered n tuples of ideal points, and of course with a distinguished first vertex, right? So ordered, but also like not it's like ordered clockwise,ly but not cyclically, right? I mean, it's kind of clockwise,ly, but I remember that there is the first vertex. And of course, if two of them give me something, if two of them give me isometric quadrilaterals, somehow I really want to identify them. So, okay, modulo the action of the group of orientation-preserving isometries. Okay, so let's see how does it look. So for the square, right? For the square, well, it's modulo Mobius transformations, right? So the first three vertices, I can decide which ones they are, because the group of because of the simply transitivity of the action of the Mobius group on triples. Right? Okay, so I can decide that my first vertex is going to be minus I, and my second vertex is going to be -1, and my third vertex is going to be I. Okay, but this guy is not transitive on 4 tuples. So I cannot decide arbitrarily which is my fourth vertex. So which means that there really is like a 1-parameter family. Right? So for instance, here you can see two ideal quadrilaterals which are not isometric, at least not under an isometry, taking this one to this one, this one to this one, and this one to this one. And according to the definition, they are distinguished as different points in the Teichmüller space of the square. Okay, and then of course, well, for the pentagon, well, now it's going to be 2-dimensional, right? Because again, I can fix my first 3 vertices, but then for the fourth one, I don't quite know, and then for the fifth one, I also don't know. And by I don't know, I mean I don't have I cannot choose it by myself, right? Okay, more generally, the Teichmüller space of the polygon is n-3-dimensional, where this 3 is the famous 3 of the transitivity of the Mobius transformations on triples. Mm-hmm. Okay, but you see, but Penner's theorem also talks about horocycles. So what I'm going to do now is I'm going to decorate the Teichmüller space. So the points in the decorated Teichmüller space are pairs consisting of a point in the Teichmüller space and a choice of horocycles based at the vertices. Mm-hmm. So for instance, if you think about the square, we already know that the Teichmüller space is 1-dimensional. So the decorated one is going to be 5-dimensional because now besides this last choice, now I also have the choice of the 4 horocycles. So it's going to be 5-dimensional. And well, more generally, now it's going to be you have n new parameters. So the decorated Teichmüller space of the polygon now is going to be n-3 plus n-dimensional. Okay, and now the thing is now if you give me a diagonal on the polygon, let's think about the quadrilateral, and let's say that you give me this diagonal, right? Since and then give me one point in the decorated Teichmüller space. Okay, in this point in the decorated Teichmüller space has a distinguished first vertex, and that is and here I use the fact that there is a distinguished third vertex to see that this diagonal induces a geodesic diagonal here, and a triangulation by geodesics. Okay, and then I can measure the corresponding lambda length and obtain a real number. So you see, each diagonal gives me a function from the decorated Teichmüller space to the real numbers, which now I think as some sort of coordinate function. Okay, and then if the magic starts with this theorem, which says, okay, now if you give me a triangulation and you look at the n functions induced by the triangulation, what you get is a full parametrization of the decorated Teichmüller space. So each triangulation gives you a full coordinatization of the decorated Teichmüller space via the lambda lengths. So via, your combinatorial diagonal induces a geodesic, and that geodesic you cut it with the horocycles and measure it. Okay, and now you see now the Ptolemy relation is a change of coordinates. Because you see, if I consider the parametrization given by this triangulation, and I perform, the combinatorial flip and obtain this one, what the Ptolemy relation tells me is the new coordinate, which would be this one, is given by this quotient. So this theorem of Penner really is a change of coordinates in a decorated Teichmüller space. Okay, and then so you see the thing is, this looks like a mutation, right? And actually, this looks like a mutation. And actually, if you draw here a quiver, as I said before, you see like where these arcs are the vertices, and you draw arrows clockwise. And then, you would obtain like one of the first examples I gave. And the mutation, we saw that it gives us precisely this. So this really is, there really is something like some cluster mutation going on there. So that's what happens. That the subring, you take the ring of all the functions that go from the decorated Teichmüller space to the real numbers, then just take the subring generated by the lambda lengths of the induced by the diagonals. That is a cluster algebra. And then people, Fogh-Goncharov, Fomin-Shapiro-Thurston, and Fomin-Thurston, they showed that all this story that I've been saying remains true for oriented surfaces with marked points. We're now kind of, instead of starting with a combinatorial polygon, you start with a real differentiable surface. Let's say compact or oriented, and maybe with boundary, and with some marked points. And you think about this differentiable surface with marked points as a combinatorial surface, and you are going to ask about all possible hyperbolic metrics that you can put on this surface in such a way that the marked points become points at infinity. And then here, I'm not going to go into the into the definition, in terms of faithful discrete representations of a Fuchsian group or whatever. I'm going to to stop there. But then the thing is, there's a whole story about the same story is true for surfaces, for oriented surfaces with marked points. So somehow the moral of this part of the story is that somehow what would be one way of thinking about what is a cluster algebra? One way of thinking is that they are coordinate rings of interesting moduli spaces. Right? I mean, Teichmüller spaces are a kind of moduli spaces. Right? So somehow that's one way. If there's something I would like you to take away from this talk is, okay, so cluster algebra. One way of thinking about cluster algebras is that they are some sort of coordinate rings of certain moduli spaces. Okay, the seeds provide coordinatizations. Each seed would provide a coordinatization, and mutations are change of coordinates. Okay. There are other ways to think about cluster algebras, but this is only one of them. I'm not saying it's the only way. It's the only thing, the only way one can think about what a cluster algebra is. Okay, and finally, let me go back to the basis, right? So in Derksen, Wiman, and Celebinsky, maybe inspired by work of Calderon-Chapoton and maybe some other authors, developed a quiver representation theoretic approach to cluster algebras, where somehow what they were looking for was a way to express cluster variables in a cluster algebra in terms of representations of quivers. To do that, they developed a mutation theory of quivers with potential, which has some parts that are like very technical. So I'm not going to go into the technical details, but somehow kind of one of the basic idea was to lift each of the three steps of quiver mutation from the combinatorial level to the algebraic level. For instance, reversing an arrow. Well, one way to lift it to the algebraic level is to think that reversing an arrow is taking a duality of vector spaces. Or taking composite arrows, one can interpret algebraically as corresponding to taking some tensor product of certain bimodules. And kind of the hard thing is to interpret, the deletion of two cycles algebraically, like to be dictated by, maybe putting the arrows of the two cycle inside some ideal. And then you would have to say, okay, which ideal? And that would be a Jacobian ideal of a potential. So, and then they would start mutating such things, right? So somehow it's kind of, the idea behind was to try to do quiver mutation, but algebraically. Okay, so a potential on a quiver is a formal combination of oriented cycles on the quiver. So example, you see here I have just, let's say, the three cycle alpha, beta, gamma. Of course, I could have taken, let's say, alpha, beta, gamma. That would be another one, where I could have taken alpha, beta, gamma plus alpha, beta, gamma square, etc. Right? I mean, so, okay, but I decide to take this one. And a quiver with potential gives rise to a Jacobian algebra via the cyclic derivatives of the potential. So, as an example, for this quiver with potential, the cyclic derivatives, I'm not going to give the definition, but basically what a cyclic derivative does is it looks for the occurrences of the arrow in the cycle, and it deletes such instance. That's pretty much what it does. And then you do that for each arrow, and then you end up with a bunch of elements of the path algebra. And then you declare those elements to be relations, to be zero relations, as in Mariano's talk. So, for instance, this would be, for instance, a gentle algebra. Okay. Here the relations. So here, this kind of this sort of little curves indicate that composition should be zero. So you see, like gamma alpha should be zero because gamma alpha is in the Jacobian ideal. Yeah, so those are the relations. Yeah. And then I just indicate them like with these little kind of segments. Yeah. Yeah. Okay. And then if you give me a representation of the quiver with potential, which really is kind of just a module over the Jacobian algebra, so a module over this quotient. Here, here I just wrote this just to see, just so that you see that things can become very technical. All right, so I mean, it's kind of this complete path algebra modulo closure of some ideal. Okay. Okay, but given such a representation, we form the F polynomial, which is a sort of generating function for the sub-representations of the representation M. So the thing is, the representation M, it consists of vector spaces attached to the vertices and linear maps attached to the arrows. And then for each dimension vector, you can form the quiver Grassmannian of that dimension vector. That is of the set of all tuples of subspaces that are stable under the linear maps, and that you call the quiver Grassmannian for the dimension vector E, and then take its Euler characteristic. And then you form the corresponding generating function. And that let's call it the F polynomial, following, here it's following Dirksen-Neumann-Celewinsky. And let's also record so somehow the F polynomial keeps track of some information about the sub-representations of M. Okay, and now let's keep track of some other piece of information about M, namely the minimal injective presentation. So take a minimal injective presentation of M, and then the injectives, you know, the zeroth injective, that is the first injective appearing in the presentation, decompose it as direct sum of indecomposables, and then and also the second one, and then record the multiplicities in a vector, and call that vector the G vector. So the G vector keeps track of how a minimal injective presentation of M looks like. For example, so let's take this quiver with potential. So let's take, you see, like a kind of a very simple representation, and actually a simple representation, right? So this representation is one-dimensional, right? So, okay, minimal injective presentation. Well, the first injective is the injective based at the vertex 2, and you take the co-kernel, and then the next one is the injective at vertex 3. So the G vector is 0, -1, 1, right? So this 1 is because here is I3, this -1 is because here is I2. And the sub-representations, well, it's simple, so it only has two sub-representations, namely the 0 sub-representation, which then gives you this 1, and itself, which then gives you the x2, because this is the vertex 2. Okay. So it's two things that keep track of some information about the representation. Okay, and then we use those two things to define certain Lagrange polynomial you see in the cluster variables of my seed. So you remember that the variables in my seed, I call them lambda 1 to lambda n. Okay, so how do we do that? Well, I take the signed adjacency quiver, the signed adjacency matrix of the quiver, which I mean, just in an example, it's defined kind of it's an adjacency matrix, right? But it keeps track of the direction, right? So this 1 keeps track of the fact that the arrow goes from 2 to 1, and this -1, the fact that from here to here, we're kind of the other way. So this is the relation between the quiver and the signed adjacency matrix. Okay, and then look at the columns, and then with each column form certain Lagrange monomial. You see here. Okay, and then consider this expression, which what it does is take the F polynomial, evaluate it in these n elements, and then take the G vector, but now as an extra exponent. So if you expand it, the final expression looks like this. Well, as an example, so you see here is the substitution. So here you get CCS of this representation. CCS of this M, so CCQS of this M would be this Lagrange polynomial, which, by the way, look, if you take this one and multiply it with lambda 2, what you obtain is, of course, lambda 3 plus lambda 1, which is, you see, lambda 3, which is an incoming, lambda 1, which is an outgoing, right? So it looks like you get some cluster variable in the cluster algebra. And then the theorem is yes, indeed, that's what happens. And then and every cluster monomial, not only cluster variables, but every cluster monomial can be obtained as such an expression for some representation of some quiver with potential. And the quiver with potential has to be somehow carefully chosen. It has to be non-degenerate in the terminology of Dirksen-Neumann-Celewinsky, and that's kind of a very long technical discussion, but okay. But the thing is, it is possible. which says, okay, so the rational functions, the cluster variables that you obtain after in the process of iteratively applying mutations, you can write them in terms of representations of quivers. That's kind of the upshot of this. Okay, so the next question is, okay, so maybe using representations, one can kind of produce a basis for the cluster algebra, right? And then kind of maybe one can say, okay, you know, if you take CCM for these representations M, for this class of representations M, you obtain a basis, right? Okay, so let's try to do a little bit of that, right? To say okay, to try to find some class of representations whose CC gives me possibly a basis of the cluster algebra. Okay, so this is going to start to be maybe a bit technical. So let's take a dimension vector, and for that dimension vector, we consider all the representations with that dimension vector, right? So because you see, when I take a dimension vector, I'm really already telling you the vector space is attached to the vertices, C to the di. Okay, and then to form a representation of the quiver with potential, now I only need to give you the tuple of matrices attached to the or linear maps attached to the arrows, and this tuple, well, it has to satisfy that it gives you a module over the Jacobian algebra. Okay, and then let's call that rep QSD, the representations of the quiver with potential of dimension vector D. This is an affine algebraic set, and as such, it splits as the union of irreducible components. And then the set of irreducible components of dimension vector D, well, I just denoted like this, here QSD. Okay, so there's a nice fact, which is if you take an irreducible component, that irreducible component contains a dense open subset on which the value of CC and the value of the G vector are constant. So you have your irreducible component, and then there is a kind of a well-defined value of CC for it, namely the value of CC at this dense open subset, which then we denote, you know, by CC of Z, and then we call it, of course, the generic Caldego-Chapoton function. And similar for the G vector. Here I think I have to mention the names of Dupont, Gais-Leclerc, Schröer, and Plamondon, who were the first ones to start working with these generic values of the CC map, of the CC function. Okay, the nicest thing that could happen, ideally what would happen is, okay, so for each dimension vector you have the irreducible components, right? For each of the irreducible components you have a well-defined value ZZ of Z, right? Okay, take those values, and then maybe that's a basis, and that would be okay, and then go home, but it's not true. They don't form up. It's not. If we do this, we obtain something which is not linearly independent. So then it's okay. So one would have to say, okay, which irreducible components do you consider? Right? If you have to exclude some because you have something which is linearly dependent, exclude some. So, and which ones do you take? So that's the next step. Right? So for the next step, one introduces something called the E invariant, which was defined by Derksen, Neumann, and Celebinsky. Well, here's the formula. I mean, I'm not going to read it for you, but maybe all I'm going to say is that this invariant turns out to have a very nice interpretation in terms of the Auslander-Reiten translation. and it's an interpretation that kind of connects very nicely to something called tau tilting theory, introduced by Adachi, Yama, and Reiten. Okay, and then in our situation, it helps us to locate what are the good irreducible components. So for an irreducible component, define certain number, which is this minimum, the minimum of the codimensions of the orbits of the orbits of the elements of the irreducible component, right? So it's some codimension, and then the thing is, it really is the generic codimension. There exists an open-dense subset where the value of this number is equal to the codimension of that orbit. Okay, so take it as some number attached to the irreducible component, that is the generic codimension. Okay, there also exists an open-dense subset where the value of this invariant is constant, right? Okay, and Guy's Leclerc-Schröer proved that one always has certain inequality. Okay, and then these two numbers help us to locate the good components. So it's those components for which both numbers are equal, and they call them the Guy's Leclerc-Schröer. They call them or initially they called them strongly reduced components. Although now I think at least Jan is more inclined to call it tau reduced because of this relation with the Outlander-Reiten translation. And then, well, now that we have a kind of a smaller set of irreducible components, then we have a new candidate for basis, which is pretty much the values of the CC at those components. Mm-hmm. And then here I'm adding the honest monomials in the original cluster, just because I have not been talking about decorations of representations, which is an extra technical ingredient, which I decided not to talk about at all. But okay. Now here kind of there's a bit of a hiccup. They called it generic basis. They called it generic basis like before proving it was a basis. And the thing is, they proved it was a basis in some cases, but not in full generality. Right? And then there is a very powerful theorem recently proved by Fan Xin, which says if the signed adjacency matrix of your quiver has full rank, so if the matrix is invertible, and the cluster algebra is injective reachable, which is some other technical condition, then this is indeed a basis. Mm-hmm. In full rank, right? In full rank. But matrices from triangulations of surfaces may fail to be of full rank. So you cannot just apply it as is to the cluster algebras arising from triangulations of surfaces, because one actually has, a way of counting the core rank of the matrix, and the core rank is given in terms of, is the sum of the number of punctures plus the number of boundary components with even number of marked points. So, for instance, if you have a triangulation of an octagon, the matrix is not going to be full rank. It's going to be of rank. Of core rank 1. Right? So you cannot apply this theorem of Fan Xin as is. Right? Okay, however, you can always find, if the surface has non-empty boundary, you can always find a triangulation with the property, so that the associated matrix, the sign adjacency matrix, has a nice property, which is there is certain set of columns which give you the rank of the matrix, and the remaining ones can be written as non-negative rational linear combination of them. Right? So okay, maybe it's not full rank, but you have rank, and then the others can be expressed non-negatively in terms of them. And this result, together with a non-trivial theorem of Plamondon on the G vectors of certain of the irreducible components. Then allows us to prove the linear independence of the generic basis, even in this situation where the matrix doesn't have full rank. Okay, and then, but so I'm not going to give you the full proof, but maybe what I can tell you is that somehow at some point we realized that if we could prove if we could prove that there exists such a tau, so that the matrix has this nice property, we would have linear independence. And then what happened is that then the problem became combinatorial. It's okay. It became okay. Just find the right triangulation, right? Which is a combinatorial problem. You can just start drawing curves, right? So okay. So in the end it became a combinatorial problem, right? So from speaking about strong, irreducible components of representation space, it became a combinatorial problem. Find a triangulation that looks like something. So maybe let me tell you give you a couple of examples. So for instance, here is an octagon, and then the corresponding matrix. And then here, I mean, you can see. I mean, this is co-rank 1. But this column is the sum of these two columns. Right? Okay, so this triangulation is the one we were looking for. And then let's say I put a puncture and then just take this triangulation. Then you compute the matrix, and then you see that the last two columns, well, they are equal among them, but they are the sum of these other two. Right? And somehow, in general, all our triangulations, kind of all the triangulations tau that we found, look like this. Look like this one looks like some sort of fan, which kind of is broken at the end, and this also looks like like some sort of fan, which is also kind of broken at the end, with a self-folded triangle. So kind of. So what I'm saying is that the triangulations we give have certain combinatorial form. And then just to finish, to show that the generic basis spans the cluster algebra, then we go to Fancin's theorem, which is for full rank, and then take one of our matrices beta, which maybe is not a full rank, somehow produce a bigger cluster algebra. So for those who know about this, is by adding some coefficients, and then in that over there we know that Fancin theorem is true, and then we specialize and then see that in our situation it also spans. So in the end, for cluster algebras associated to surfaces with marked points, possibly punctured, but with non-empty boundary, at the end, the generic basis is indeed a basis. And thank you.
So we thank the speaker. Are there some questions? Let me say, the first time I heard about mutations was for works involving bundles over projective spaces. For example, the work of Drezé and Le Potier in the 80s, and then work of Bondal and so on. And probably this is a kind of example of quiver representation. Do you know exactly?
No, I'm not. No, I don't know. Yeah. I mean, I don't know. I don't know what would be kind of the interpretation. Yeah, no, I don't know.
Are there more questions? So if we don't have more questions, we'll thank the speaker again.